So, here's something that might surprise you. The device playing this voice to you right now is solving equations, thousands of them, every second. To turn a stream of stored numbers back into the sound of a human voice, it is quietly working out unknown values, over and over, filling in the spaces between the things it already knows. Every small adjustment to the volume, every curve of the sound wave reaching your ears, is the answer to a tiny question that begins with the words, "What number goes here?" That is algebra. It is happening in your hand, right now, while you lie still in the dark. Tonight we're going to go through all of algebra, from the very beginning, the history, the core ideas, all the way through to how it works today. We'll start thousands of years ago, with people pressing marks into wet clay, trying to divide land and grain fairly. We'll move slowly through the centuries, watching one idea quietly stack on top of another, until we arrive at the strange and beautiful thing algebra has become. By the end, you won't just know that algebra exists, you'll understand what it actually is, what a variable really means, why an equation is a kind of balance, how a single unknown letter became one of the most powerful ideas ever invented by human beings. And you'll understand it the way you understand a story you've heard told gently, not the way you were forced to learn it in a classroom. If you fall asleep somewhere along the way, that's perfectly fine. That's the point. The ideas will still be here if you want to come back. Nothing tonight is going on a test. There is nothing to memorize, nothing to get right. You can let the words blur and drift, and you'll still absorb more than you expect. So settle in, let your shoulders drop, let the weight of the day go soft. We have a long, slow walk ahead of us, and there is no hurry at all. Let's begin where algebra begins, which is much earlier than most people imagine. Long before there were letters standing in for numbers, long before there were equal signs or textbooks, there were people with a very practical problem. They had things to count and things to share, and things they did not yet know. Picture the land between two great rivers, the Tigris and the Euphrates, in what we now call Iraq. Around 4,000 years ago, the people there, the Babylonians, built one of the first great civilizations. They had cities and temples and trade. And to run all of that, they needed mathematics, not for its own sake, but to survive. They needed to measure fields. They needed to divide an inheritance among sons. They needed to work out how much grain a granary could hold, and how many workers it would take to dig a canal, and how to split a debt. These are ordinary problems. But hidden inside them was something extraordinary. The Babylonians wrote on clay. They took a soft tablet of river clay, and pressed marks into it with a reed cut to a wedge shape, and then let the clay dry hard in the sun. Because of that, their mathematics survived. Tablets that were written 4,000 years ago can still be read today. Sitting in museums, the little wedge marks still sharp. We have thousands of them. And on many of these tablets are mathematical problems, not theory, problems. A question, and then a worked answer, step by step, the way a teacher might show a student. Here is the thing that matters about those problems. Some of them involved a quantity that the Babylonians did not know yet, and were trying to find. They would describe a situation, the length of a field, multiplied by itself, plus the length again, comes to a certain total. Find the length. Now stop and notice what that is. They had a number they did not know, the length of the field. They had a relationship that the number had to obey, and they had a procedure for working backward from the relationship to the number itself. That is the beating heart of algebra, a hidden number, a rule it must follow, and a path to uncover it. The Babylonians were doing this 2,000 years before the birth of Christ, but they did it without any of the tools you might recognize. There was no letter standing for the unknown. There was no symbol for plus or minus or equals. They wrote everything out in words, in the same way you might tell a story. Take the number, multiply it by itself, add the number again, and so on. Their mathematics was entirely verbal and entirely tied to recipes. A scribe would learn a procedure by heart, the way you might learn how to cook a familiar meal, and apply it to whatever numbers the problem gave him. They were not proving anything. They were not asking why the procedure worked. They simply knew that it did, because it always had. They also counted in a way that feels strange to us now. We count in tens, because we have 10 fingers. The Babylonians counted in 60s. It sounds awkward, but it has quietly survived into your own life. The reason there are 60 seconds in a minute, and 60 minutes in an hour, and 360 degrees in a circle, is the Babylonians. When you glance at a clock tonight, you are reading numbers in a system 4,000 years old. The base of 60 had a quiet advantage. 60 can be divided evenly by 2, 3, 4, 5, and 6, which made splitting things into parts much easier. For a civilization built on dividing land and grain and labor, that mattered. There is one tablet in particular, kept now at Columbia University, known by the dull name Plimpton 322. It is a small clay tablet, broken on one edge, with columns of numbers carved into it. For a long time, no one was sure what it was. But the numbers, when you look closely, form a pattern. They are related to right triangles, to the relationship between the sides of a triangle with a square corner. The Babylonians, it seems, had worked out a deep numerical pattern more than 1,000 years before the Greek thinker Pythagoras was born, the man whose name we now attach to it. They did not write it as a rule, the way we would. They wrote it as a table of examples. But the understanding was there, pressed into the clay. Now travel west, to Egypt, along the green ribbon of the Nile. The Egyptians, around the same era, had their own mathematics and their own way of recording it. Instead of clay, they wrote on papyrus, a kind of paper made from a reed that grew along the river. One famous document, the Rhind Papyrus, named after the Scottish man who bought it in the 1800s, is a kind of mathematical handbook, copied out by a scribe named Amos around 3,600 years ago. Amos tells us, in his own words, that he is copying from an even older text. So the knowledge was already ancient when he wrote it down. The Egyptian problems have a charm to them. Many of them deal with an unknown quantity, which they called aha, a word that simply meant a heap or a pile. A heap and a seventh of the heap added together make 19. What is the heap? You can feel the algebra in that. There is a hidden amount, the heap, and a rule it obeys, and a question asking you to find it. The Egyptians had a clever way of solving such problems, which we now call the method of false position. The idea is gentle and almost playful. You do not know the heap, so you simply guess a convenient number. You try it, you see how wrong your guess is, and then you scale your guess up or down by exactly the right factor to fix the error. It is solving by intelligent guessing, by feeling your way toward the answer rather than charging straight at it. And it works. So already, in two of the earliest civilizations on Earth, separated by deserts, we find the same quiet idea appearing. The idea of a number you do not yet know, that you are trying to find, by following the rules it must obey. Neither the Babylonians nor the Egyptians had a name for this idea. They did not think of it as a single thing. It was just something you did when a problem needed it. The recognition that all these problems shared a common shape, that they were all really the same kind of problem in different clothing, would take a very long time to arrive. That recognition is the story of tonight. Let's rest there for a moment, with those ancient scribes, pressing reeds into clay and brushing ink onto papyrus, working out the size of fields by the slow light of the sun. They were not trying to invent algebra. They had no idea they were standing at the beginning of anything. They were just trying to share a harvest fairly and keep the records straight. Sometimes the largest ideas in human history begin like that, quietly, in the hands of people solving small and ordinary problems. Now we come to the question that, more than any other, pushed all of this forward. Because for a very long time mathematics had a strange and limiting habit. It was tied, very tightly, to specific things. A Babylonian scribe could solve a problem about a particular field of a particular size. An Egyptian scribe could find a particular heap. But each problem was its own little island. If the numbers changed, you started again. There was no general method that said, Here is how to solve every problem of this kind, no matter what the numbers are. Every answer was a one-time answer, and that meant mathematics could not really grow beyond the patience of the person doing it. Think about what was missing. Imagine you know how to bake one specific loaf of bread, because someone showed you step by step with exact amounts. Now imagine you want to bake a larger loaf, or a smaller one, or a loaf with different flour. Without a general recipe, without understanding why the steps work, you are lost. You would have to be shown all over again. What mathematics needed in order to grow was the recipe itself, the general pattern, the method that holds true no matter what specific numbers you pour into it. And to write down a general pattern, you need a way to talk about a number without saying which number it is. You need to be able to say, take any number and call it this, and here is what to do with it. That ability to speak about a number in general is the thing that had not yet been born. There was a second problem too, just as deep, and it was about what counted as a real number at all. The ancient world was suspicious of certain kinds of numbers that we now use without a second thought. Negative numbers, for one. The idea of a number less than nothing seemed absurd to many ancient thinkers. How can you have less than nothing? If you have 3 sheep and you take away 3 sheep, you have no sheep, and that is the end of it. The notion of having -2 sheep was not a quantity. It was nonsense. And so for centuries, when a problem led to a negative answer, mathematicians would simply throw it away, or declare the problem impossible, or rearrange it to avoid the negative entirely. Zero itself was a problem. It seems almost impossible to believe now, when zero is everywhere, but for most of human history there was no number zero. There was the absence of a thing, yes, but not zero as a number you could calculate with, a number that sat on the number line like any other. The leap to treating nothing as something, as a number you could add and subtract and use in equations, was one of the great quiet revolutions of human thought, and it happened far from Europe, which we will come to. So picture the situation. Mathematics could solve individual problems, but not families of problems. It had no general language for an unknown quantity. It was suspicious of negative numbers, and it had not fully accepted zero. And yet, pressing against all these limits, the practical needs of the world kept growing. Trade was expanding. Empires needed to tax and to build. Astronomers needed to predict the movement of the stars and the seasons, which mattered enormously for agriculture and for religion. Every one of these activities threw up problems with hidden quantities in them. The pressure was building. The tools were not yet ready. And into that gap, slowly, across several different civilizations, the real machinery of algebra began to form. The first steps toward a general language came from a man working in the city of Alexandria, in Egypt, around 1750 years ago. His name was Diophantus. We know almost nothing about his life. There is a famous riddle, written long after his death, that claims to encode his age at various life events. And if you solve it, which is itself a little algebra problem, it suggests he lived to be 84. Whether that is true or just a charming legend, no one can say. But what he left behind was a collection of books called the Arithmetica, and it changed things. Diophantus did something that had not quite been done before. He began to use abbreviations. Instead of writing out every word of a problem in full, every single time, he developed shorthand symbols for the unknown quantity, and for its powers, and for subtraction. It was not the clean symbol system you know today, but it was a step toward it. It was the difference between telling a long story out loud and beginning to write it down in a faster, more compact hand. Because of this, historians sometimes call his work syncopated algebra, meaning algebra that is partway between full words and full symbols. He had one foot in the old world and one foot in the new. But Diophantus was still working problem by problem, and he still avoided negative numbers, treating them as meaningless. When his calculations produced a negative, he called the problem absurd. So he had taken a real step toward a general language, but he had not freed himself from the old suspicions, and his work, brilliant as it was, sat for centuries without being fully built upon in the place where he wrote it. The torch, for a while, passed elsewhere. It passed east, to India, where some of the most important pieces of the puzzle were quietly put into place. In India, mathematicians made two enormous contributions, and both of them concern the very nature of number. The first was zero. Indian mathematicians were the ones who fully embraced zero as a number in its own right, not just a gap or a placeholder, but a genuine quantity that you could add, subtract, and calculate with. The second was the full acceptance of negative numbers. Where the Greeks had recoiled, Indian mathematicians leaned in, and they had a beautifully practical way of thinking about it. They thought of positive numbers as money you have, as fortunes, and negative numbers as money you owe, as debts. A debt is real. You can hold a debt in your mind perfectly well. You can add debts together and subtract them, and the arithmetic behaves sensibly. With that single shift of imagination, negative numbers stopped being nonsense and became simply another kind of quantity, a direction, rather than an impossibility. The mathematician most associated with writing these ideas down is Brahmagupta, who lived in the 7th century, around 1400 years ago. In a major work, he laid out rules for arithmetic that included zero and negative numbers, explaining how positives and negatives combine, how a debt and a fortune cancel, how two debts make a larger debt. He also gave a general method for solving a certain important family of equations, the ones we now call quadratic, where the unknown appears multiplied by itself. And here is the quiet revolution. Brahmagupta's method was general. It worked for the whole family at once, including cases that produced negative answers, which he was willing to accept. He was no longer solving one field, one heap, one island. He was solving every problem of a certain shape, in a single stroke. The recipe itself was finally being written down, so as we move toward the great turning point, hold these pieces in your mind, loosely, the way you would hold sand. From Babylon, the ancient instinct to find a hidden number by the rules it obeys. From Egypt, the gentle art of guessing and correcting. From Diophantus in Alexandria, the first shorthand symbols, the first move from words toward signs. And from India, the two missing numbers, zero and the negatives, and the beginnings of truly general methods. All of these threads were lying about, in different lands, in different languages, waiting. What was needed now was someone to gather them, to weave them together, and to give the whole thing a name. That is exactly what happened next, in one of the greatest cities of the medieval world. The city was Baghdad, and the time was the early 9th century, around 1200 years ago. Baghdad was then the capital of a vast empire, and at its heart was a center of learning that has come down to us by the name the House of Wisdom. It was a place where scholars gathered, where books from many civilizations, Greek and Indian and Persian, were collected and translated and studied. Imagine a great library and academy combined, full of people whose entire purpose was to gather the knowledge of the world and build upon it. Into this place came a scholar, whose name you should hold gently tonight, because more than anyone else, he is the reason the word algebra exists. His name was Muhammad ibn Musa al-Khwarizmi. Around the year 820, al-Khwarizmi wrote a book whose title contains two Arabic words that matter very much. The words were Algebra and al-Muqabala. Algebra is the word that became, through Latin and centuries of use, our word algebra. And its meaning is lovely, and it tells you something true about the subject. Al-Jabr means restoration or completion. It refers to the act of taking a quantity that has been subtracted on one side of a problem and restoring it by moving it to the other side, so that everything is whole and positive again. The companion word, al-muqabala, means balancing or reduction, the act of canceling equal things on both sides to simplify what remains. So at the very root of the word algebra is a physical, almost bodily idea. The idea of moving things from one side to another and keeping both sides in balance. Restoration and balancing, hold on to that, because it is the secret of the whole subject, and we will return to it again and again tonight. What al-Khwarizmi did, that no one had quite done before, was to treat the solving of equations as a subject in its own right, not as a collection of tricks for specific problems, but as a general system, with general methods laid out in order, explained step by step, with reasons. He took the family of problems where an unknown appears, and where it sometimes appears multiplied by itself, and he sorted them into types, and for each type he gave a complete method that would always work. He even gave geometric demonstrations, drawing squares and rectangles, to show why his methods were correct, not merely that they were. He was not just solving problems, he was explaining the machine that solves them. There is a detail here that is easy to pass over, but is quietly important. Because al-khwarizmi, like the Greeks before him, was still uneasy with negative numbers, he could not simply write every equation in one tidy form, the way we do today. To avoid ever showing a negative number, he had to split what we would see as one kind of problem into 6 separate types, depending on which terms appeared on which side. It seems like extra work, and it was. But it shows you something about how mathematics grows. Even the man who gave algebra its name was still carrying the old caution about negatives. The same caution we traced back through the Greeks. The full freedom to use negative numbers everywhere, which would have collapsed his 6 types into one, was still arriving. Ideas come in pieces, and the pieces arrive in their own time, carried by different hands. His name carries a second gift too. When al-Khwarizmi's works were later translated into Latin, his name itself was Latinized, written as algorithmi. And from a man's name worn smooth by centuries of European tongues, comes our word algorithm. So this one scholar, working in Baghdad 1200 years ago, gave us not one but 2 of the foundational words of the modern world: algebra, the art of the unknown, and algorithm, the idea of a step-by-step procedure that always reaches its answer. Every time you hear the word algorithm now, attached to a phone, a website, a piece of software, you are hearing a faint echo of a man bent over his work in the house of wisdom, sorting equations into types and explaining, patiently, exactly how to solve each one. Let your mind rest on that image for a while. The library at the center of the world. The translated books from distant lands stacked on the tables. The careful work of gathering what others had found and shaping it into something whole. Al-Khwarizmi did not invent the unknown number. The Babylonians had it. He did not invent 0 or the negatives. India gave us those. He did not invent the first symbols. Diophantus reached for those. What he did was bring the threads together and recognize that they formed a single subject, worthy of a name, worthy of a system. That act of recognition, of seeing the one idea behind the many problems, is itself one of the deepest acts in all of mathematics. And it is why, when we name the father of algebra, his is the name we most often say. If you're still with me, let your eyes close now if they aren't already. You don't need to follow every word from here. Just let it wash over you. The explanation continues either way. Now we begin to build, slowly, on the foundation al-Khwarizmi laid, because the centuries after him saw his single idea grow new branches, one at a time. The first thing that happened was that other scholars in the same broad tradition pushed his ideas further, and in particular they began to loosen algebra's tie to geometry. Al-Khwarizmi had leaned on pictures of squares and rectangles to justify his methods. But a quantity multiplied by itself does not have to be thought of as the area of a literal square. It can be thought of purely as a number operation, an arithmetic act, with no picture attached. A scholar named al-Khwarizmi, working a little later, took important steps in this direction, treating the unknown and its powers as objects you could manipulate by pure arithmetic rules, stacking higher and higher powers, the unknown times itself, and again, without needing to imagine a shape for each one. This was a quiet but significant freeing. It let algebra climb beyond the 3 dimensions of physical space, into powers that no drawing could capture. Then there was the poet. In the late 1100s, in Persia, lived a man you may know for his verses, a writer of quatrains, short 4-line poems about wine and time and the fleeting nature of life. His name was Omar Khayyam, but Khayyam was also a serious mathematician and astronomer, and he turned his attention to a harder class of problems than the ones al-khwarizmi had fully solved. Al-khwarizmi had mastered equations where the unknown appears multiplied by itself, the squared problems. Khayyam went after the next level up, the ones where the unknown is multiplied by itself twice over, what we call cubic equations, problems involving the unknown cubed. He could not find a tidy formula for them. No one could, for centuries more. But he found something beautiful instead. He found that you could solve them geometrically, by drawing curves, particular curves like those you get by slicing through a cone and looking at where they cross. The crossing point gave the answer. It was a bridge between the world of equations and the world of shapes, and it showed that the two were secretly speaking about the same things. While all of this was unfolding in the Islamic world, Europe had been comparatively quiet in mathematics for a long stretch. But trade was about to carry the new ideas across the Mediterranean. In the year 1202, an Italian merchant's son, who had traveled widely around the trading ports of North Africa and the Middle East, published a book that would slowly transform European mathematics. His name was Leonardo of Pisa, though he is far better known by a nickname given to him much later, Fibonacci. As a young man traveling among the markets of the Mediterranean, Fibonacci had seen the Hindu-Arabic system of numerals in use, the very digits you write today, 0 through 9, with their clever place value system where the position of a digit tells you its size. He saw at once how vastly superior this was to the clumsy Roman numerals still used in Europe, where there was no zero, and where simple arithmetic was a genuine struggle. His book argued, with many worked examples drawn from the real business of trade, that Europe should adopt these numerals. It took a long time. Merchants were cautious, and some cities even banned the new numerals for a while, fearing they were too easy to alter fraudulently. But slowly, over generations, the new digits won, because they were simply better. And without those numerals, with their zero and their place value, the algebra that was coming would have been nearly impossible to write down clearly. So Fibonacci, remembered today mostly for a sequence of numbers that bears his name, did something far more important for our story. He helped give Europe the very symbols in which the next great chapter of algebra would be written. That chapter, the dramatic one with secrets and rivalries and a contest that played out in public, was waiting just a few centuries ahead, in the cities of Renaissance Italy. And that is where we will go next, once you have had a moment to let all of this settle, here in the quiet, with the long history of the unknown number drifting slowly through your mind like weather over a calm sea. So picture Italy in the early 1500s. The Renaissance is in full bloom. Art and learning are alive in the city-states of Florence and Venice and Bologna. And among the mathematicians of the time, there was a problem that had resisted everyone for centuries. It was the cubic, the problem where the unknown is multiplied by itself twice over. Omar Khayyam had found a way to solve it, with curves, geometrically, but no one had found a clean formula, a recipe in numbers alone, the way al-khwarizmi had given a recipe for the squared problems. It was the great unsolved puzzle of the age. And the story of how it was finally cracked is not a quiet story of scholars sharing freely. It is a story of secrecy and rivalry and a public contest and a betrayal that left two men as enemies for the rest of their lives. The first to find a piece of the answer was a man named Scipione del Ferro, a professor at the University of Bologna. Sometime in the early 1500s, he worked out how to solve an important type of cubic. And then he did something that seems strange to us now but made perfect sense in his world. He told no one. In those days, a mathematician's position could depend on public contests, where two scholars would challenge each other with problems, and the one who solved more would gain reputation, and sometimes the loser would lose his job. So a secret method was a weapon. Del Ferro guarded his solution for years, and only on his deathbed did he pass it quietly to one of his students, a man named Antonio Maria Fiore. Now Fiore was not a great mathematician, but he held this one powerful secret, and he decided to use it. He challenged another scholar to a public contest. That other scholar was a poor, self-taught man from Venice named Niccolo Fontana, known to everyone by a cruel nickname, Tartaglia, which means the stammerer, because a wound from his childhood, a sword cut to the face from invading soldiers, had left him with difficulty speaking. Tartaglia was brilliant and proud, and had clawed his way up from poverty through sheer ability. And in the run-up to the contest, working alone, under the pressure of the challenge, he managed to rediscover the solution to the cubic for himself, and even to extend it further than Fiore could. When the contest came, Tartaglia solved every problem Fiore set him, and Fiore could not return the favor. Tartaglia won completely. Word of his triumph spread, and it reached the ears of a remarkable and difficult man named Girolamo Cardano. Cardano was a physician, an astrologer, a gambler, and a mathematician, a man of enormous talent and enormous flaws, whose life was full of brilliance and disaster in equal measure. Cardano wanted that solution. He wrote to Tartaglia, and pleaded and flattered, and eventually persuaded Tartaglia to share the method. But Tartaglia would only do it under a solemn oath. Cardano had to swear never to publish it, and so Tartaglia handed over his secret, encoded, fittingly, as a poem, the steps of the method hidden in verse, so that they could be remembered and kept close. For a while Cardano kept his oath, but then he and his own gifted student, a sharp young man named Lodovico Ferrari, made a discovery. They learned that Del Ferro, the professor in Bologna, had found the solution first, years before Tartaglia. They even traveled to see Del Ferro's old notebook, with the method written in his own hand. And Cardano reasoned, perhaps conveniently, that his oath had been about Tartaglia's solution, but the credit truly belonged to Del Ferro, who had found it earlier and was now dead. So in the year 1545, Cardano published a great book on algebra, and in it he laid out the solution to the cubic for all the world to see. He did give credit to both Del Ferro and Tartaglia by name, but Tartaglia was beside himself with fury. He felt betrayed, his life's secret given away against a sworn promise. A bitter public quarrel followed, with insults and challenges flying between Tartaglia and the loyal Ferrari, and it poisoned the rest of Tartaglia's life. He died feeling cheated, but the mathematics, once released, could not be put back, and it had a strange and lasting gift inside it, because in solving cubics, mathematicians kept running into something that should not have existed. They kept needing to take the square root of a negative number. Now you know that a negative number, by the old understanding, has no square root, because any number multiplied by itself gives a positive result. A positive times a positive is positive, and a negative times a negative is also positive. So nothing, multiplied by itself, gives a negative. The square root of a negative seemed to be pure nonsense, a door that opened onto nothing. And yet, in the middle of solving a perfectly real cubic with perfectly real answers, these impossible roots would appear, and then, if you were brave enough to carry them along through the calculation, they would cancel out at the end and leave you with the correct, sensible, real answer. They were like ghosts that did real work. Cardano noticed them and called them subtle and useless. But others, a little later, a mathematician named Raphael Bombelli chief among them, took them seriously and worked out rules for how they behaved. These ghost numbers, the square roots of negatives, would eventually be called imaginary numbers, a name that was meant as an insult and stuck forever. And centuries later, they would turn out to be among the most useful numbers in all of physics and engineering, woven into the description of electricity and light and the strange rules of the very small. But that is a longer story, for another night. Now, with the cubic solved, and the imaginary numbers glimpsed, algebra was straining against its own clothing, because all of this was still being written out in a clumsy mix of words and half-symbols. To make the next leap, algebra needed a proper written language of its own. It needed clean, simple signs that anyone could read at a glance. And over the next century or so, in a few quiet strokes, that language was finally built. This is one of the gentlest and most underappreciated parts of the whole story, because the symbols you take for granted, the ones that probably gave you trouble in school, were each invented by a particular person, at a particular time, for a particular reason. Start with the simplest and most important sign of all, the equals sign, those two short parallel lines. Before it existed, people wrote out the word equals, or some abbreviation of it, every single time. Then in the year 1557, a Welsh physician and mathematician named Robert Recorde, writing a textbook with the wonderful old title, The Whetstone of Witta, grew tired of writing the same word again and again. So he invented a symbol for it. He chose two short parallel lines, and he explained his reasoning beautifully. He said that no two things could be more equal than a pair of parallel lines of the same length, because they are forever the same distance apart, never meeting, never drifting. So the next time you write that sign, remember the gentle logic behind it. Two lines, side by side, perfectly matched, standing for the idea of balance itself. A little before and around this time, the signs for plus and minus had also come into use, growing out of marks used by merchants and in German arithmetic books, the small cross for adding and the short dash for taking away. And then came a Frenchman who took the boldest step of all in the building of this language. His name was François Viète, working in the late 1500s. Viète had an idea that sounds small but was enormous. Up to this point, even when people used a symbol for the unknown, they still wrote the known numbers in a problem as actual numbers. So a method was always tied to specific values. Viète said, "Let us use letters not just for the unknown, but for the known quantities too, the ones that might be anything. Let a letter stand for the number we are looking for, and let other letters stand for whatever fixed numbers the problem happens to have." With that, you could write down a method, a whole general recipe, entirely in letters with no specific numbers in it at all. You could finally write the recipe itself, pure and general, freed from any particular case. This was the true arrival of the thing the ancient world had been missing, the ability to speak about numbers in general, in writing, cleanly. It is hard to overstate how much this opened up. It was the moment algebra gained a fully general voice, and then the language was brought into its final familiar form by a man you may know better as a philosopher, René Descartes, in a work published in the year 1637. Descartes gave us several habits we still follow without thinking. He used letters from the end of the alphabet, the X and the Y and the Z, for the unknowns, the things we are solving for, and letters from the start of the alphabet, the A and the B and the C, for the known quantities. That is why, to this day, the unknown in a problem is so often called X. It is a habit nearly 400 years old, set down by Descartes. He also gave us the neat way of writing powers, the small raised number that tells you how many times a quantity is multiplied by itself, so that you no longer had to invent a separate symbol for the square and the cube and beyond. And he did one more thing, perhaps the deepest of all, which we will come back to later tonight, when we talk about how algebra and geometry were joined together into a single landscape. For now, simply hold the picture of the language being completed. From Recorde's two parallel lines, to Viète's letters for the knowns, to Descartes laying down the X and the Y and the raised powers. By the middle of the 1600s, algebra finally looked, on the page, the way it looks to you now. And here is where we can slow right down, and turn from the history of who did what to the heart of the matter. Because now that the language exists, we can actually look at what algebra is, underneath all the names and dates. We can look at the machine itself and see how it works. So let the history drift to the back of your mind for a while. Let the scribes and the scholars and the feuding Italians fade gently into the dark, and let us look, slowly and plainly, at the simple and powerful ideas that all of that history was reaching toward. Begin with the single most important idea in all of algebra, the idea of the variable. A variable is just a letter that stands in for a number. That is all it is. But there are two slightly different ways it can stand in, and it helps to feel the difference between them. Sometimes a letter stands for a specific number that we do not happen to know yet, a number that is fixed and waiting to be found, like a name written on a sealed envelope. The number is real and definite. We simply have not opened the envelope. Other times, a letter stands for a number that is free to change, that can take many values, sliding up and down a range, and we are interested in how other things respond as it moves. The same little letter can play either role. In one problem, the X is a hidden treasure with one true location. In another, the X is a dial we are free to turn. Both of these are what we mean by a variable, a number held loosely, a number we are reasoning about without pinning it to one fixed value in advance. The whole power of algebra comes from this willingness to reason about a number before you know what it is. To hold the unknown in your hand and work with it anyway. Once you have a variable, you can build things out of it, and the simplest thing you can build is called an expression. An expression is a little recipe made of numbers and variables joined by operations, by adding and subtracting and multiplying and dividing. Something like a number plus 3, or twice a number taken away from 10. An expression is a phrase, not a sentence. It describes a quantity, but it does not make a claim. It is like the words "a warm loaf of bread." That phrase points at something. It describes it, but it does not assert anything to be true or false. You cannot agree or disagree with the phrase "a warm loaf of bread." It just sits there, naming a thing. An expression is the same. It names a quantity, built out of the variable, but it does not yet say anything about it. To make a claim, you need an equation, and this is where algebra comes alive. An equation is two expressions set equal to each other, with that parallel lined equals sign between them, the one Robert Ricord gave us. An equation is a full sentence. It makes a definite claim. It says, this quantity over here and that quantity over there are exactly the same in size. They balance. And the moment you write an equation with an unknown in it, you have posed a question to the universe. You have said, there is some value, some specific number that the unknown could be, that would make this balance true. Find it. That is the whole game. An equation is a balance that is true for only certain values of the unknown, and solving it means finding those values, finding exactly the numbers that make the two sides weigh the same. Now hold that word, balance, because it is the secret of everything, and it is the very thing hidden in the ancient word algebra, restoration and balancing, that we met long ago tonight in Baghdad. The best way to picture an equation is as an old-fashioned set of scales, the kind with two pans hanging from a beam, one on the left and one on the right. The equal sign is the central pivot. Whatever sits in the left pan weighs exactly the same as whatever sits in the right pan, because that is what the equal sign promises. The two sides are in perfect balance. And now here is the one rule, the single rule, that lets you solve almost any equation you will ever meet. If the two pans are balanced, and you do the very same thing to both pans at once, they stay balanced. If you add the same weight to both sides, they stay level. If you take the same weight off both sides, they stay level. If you double everything in both pans or halve everything in both pans, the balance holds. Whatever you do, as long as you do it equally to both sides, the equality survives. The balance is preserved. That single rule is the engine of algebra, and once you truly feel it, a great deal of the fear of the subject falls away. Because solving an equation is nothing more than carefully changing both sides, the same way each time, step by step, until the unknown is left sitting all alone on one side, with its value revealed plainly on the other. You are not doing anything clever or magical. You are simply tidying. You are peeling away everything that surrounds the unknown, one layer at a time, always doing the same thing to both pans so the balance never breaks, until at last, the unknown stands by itself and tells you what it is. Let us walk through that feeling slowly, with a gentle example, no rush at all. Suppose someone tells you that some number, tripled and then with 2 added on, comes to 14. We do not know the number yet, so we give it a letter, and we write the claim down as an equation. On the left pan we have the number tripled, with 2 added. On the right pan we have 14. The two pans balance. Now we want the number alone, but it is buried. It has been tripled, and it has had 2 added to it. So we undo those things, gently, in the reverse order they were done, always to both sides. First, we take away the 2. We lift 2 units of weight off the left pan, and to keep the balance, we lift 2 units off the right pan as well. Now the left pan holds just the number, tripled, and the right pan holds 12. The balance still holds. We are nearly there. The number is now only tripled, so we share out both pans into 3 equal parts and keep just 1 part of each, which is the same as dividing both sides by 3. 1/3 of the left pan is simply the number itself. 1/3 of 12 is 4, and there it is. The number is 4. The unknown has been uncovered, not by guessing, not by luck, but by patient, balanced tidying. And if you ever doubt it, you can pour the 4 back into the original claim and check. 4, tripled, is 12, and 2 added on makes 14, exactly as promised. The balance was true all along. That small example holds within it the entire spirit of the thing. Notice what we did. We undid the operations in reverse order, the way you take off your shoes before your socks, even though you put your socks on first. We always acted on both sides equally, so the balance was never broken, and we kept going until the unknown stood alone. This kind of equation, where the unknown appears only by itself, never multiplied by itself, is called a linear equation, and it is the simplest and most common kind. The word linear is connected to the word line, and there is a lovely reason for that, which we will reach when we talk about pictures of equations a little later. For now, just feel how calm and certain the process is. There is no cleverness required, only patience, and the steady habit of treating both sides alike. Restoration and balancing. The ancient idea alive in your hands. Before we step up to harder equations, it is worth pausing on the part of algebra that is, in truth, the most human of all, and the part that machines are still least able to do for us. Because everything we just walked through, the balancing, the tidying, the uncovering of the unknown, is the mechanical part, the part a calculator or a computer can now do in an instant. But there is an earlier step, a quieter and more difficult one, that comes before any solving can begin. It is the act of taking a situation in the real world, described in ordinary words, tangled and human and vague, and turning it into a clean equation in the first place. This is called translation or modeling, and it is the true art at the heart of the subject, the bridge between the world of meaning and the world of rules. Let me show you what I mean, slowly. Suppose someone tells you a little riddle, in plain words. I am thinking of a number. If I double it and then add 7, I get the very same result as if I had tripled it and then taken away 3. Find my number. Now, before any balancing can happen, you have to perform a small act of magic, so quiet you might not notice it is magic at all. You have to give the unknown number a name, a letter, and then walk through the sentence phrase by phrase, turning each piece of ordinary language into a piece of symbol. Double it becomes 2 of the unknown. Add 7 becomes, simply, with 7 more. I get the same as becomes the equals sign, the balance, the 2 parallel lines. Tripled becomes 3 of the unknown. Taken away 3 becomes with 3 removed. And when you have walked all the way through the sentence in this way, translating as you go, you find that the riddle, which was a knot of words, has become a clean and simple equation, 2 expressions set equal across the balance. And from there, the work is exactly the patient tidying we just practiced, undoing and balancing until the unknown stands alone and tells you it was 10 all along. But notice where the real difficulty lay. It was not in the solving was mechanical, almost automatic. The difficulty and the artistry was in the translation, in the turning of the human sentence into the symbolic one. That is the step that takes understanding. That is the step that is genuinely hard and genuinely creative, and that no machine does nearly as well as a thoughtful person. This is what scientists and engineers are really doing, underneath all their equations. They are translators. An engineer looks at a real bridge, with its real steel and its real loads, and renders it as a system of equations, a faithful little model of the true thing, capturing its essential bones in symbols. A physicist looks at a planet swinging around a star and writes down equations that stand in for that motion. An economist looks at the churn of buyers and sellers and finds equations that mirror its shape. In each case, the equation is not the thing itself. It is a model of the thing, a translation of the relevant part of reality into the language where the rules of algebra can take over and grind out an answer. And then, once the answer is found in the world of symbols, it must be translated back, carried home across the bridge, and read once more as a fact about the real bridge, the real planet, the real market. The unknown that came out as 10 becomes, back in the world, the right length for a beam, or the time a planet takes to circle, or the price at which a market settles. This round trip, from world to symbol and back to world, is the deepest use of algebra there is, and it is the thing the whole long history was reaching toward. Not merely to solve equations, but to let us write down pieces of the world as equations in the first place, so that the patient rules could be turned loose on reality itself. There is one more quiet thing this art gave us, and it is a kind of certainty that the ancient world never fully had. For most of the early history we trace tonight, algebra was a collection of recipes. Do this, then this, then this, and the answer appears. The recipes worked, reliably, but for a very long time no one proved exactly why they worked, or whether they would keep working in every imaginable case. They were trusted because they had been tried many times and never failed. But once the language of letters arrived, the language of Viet and Descartes, where a single letter could stand for any number whatsoever, something deeper became possible. You could now prove that a method worked, not just for the particular numbers you happened to test, but for every number at once, forever. In all the infinite cases you could never test one by one. By reasoning with the letters, which stood for anything, you could show with full certainty that a balance would always come out right, that a formula would never fail, that a pattern would hold in every case there could ever be. This is the idea of proof, of certainty earned through reasoning rather than mere trial, and it lifted algebra from a craft of reliable recipes into a body of certain knowledge. There is a deep restfulness in that, if you let yourself feel it. The answers algebra gives are not merely usually right, not merely right so far. Where they are proven, they are right with a completeness that nothing in the ordinary world can match. True in every case, true forever, true in a way that does not depend on anyone checking. A small, perfect certainty in an uncertain world. Now let us step up, gently, to the next kind of equation, the kind that troubled the ancient world and gave al-khwarizmi his 6 careful types. This is the kind where the unknown is multiplied by itself. We call this a squared quantity, and the reason for that word is worth pausing on, because it is a little doorway back into the earliest history of tonight. When you multiply a number by itself, you can picture it as the area of a square whose sides are that length. A side of 3, multiplied by a side of 3, gives an area of 9, a square 9 units in size. That is why a number multiplied by itself is said to be squared. The word comes from the literal shape. The Babylonians thought this way, and al-khwarizmi drew actual squares to justify his methods. The geometry was never far away. When the unknown appears squared in an equation, mixed perhaps with the plain unknown and an ordinary number, we call the whole thing a quadratic equation, from a Latin root that also points back to the 4-sided square. Quadratic equations behave differently from the linear ones, and the difference is quietly profound. With a linear equation, there is usually just one answer, one value that makes the balance true. But with a quadratic, there are usually two different numbers, both of which satisfy the equation, both of which make the 2 pans weigh the same. And the reason there are 2 is hidden in the act of squaring itself. Think about what numbers, when multiplied by themselves, give you 4. The obvious answer is 2, because 2 times 2 is 4. But there is a second answer, and it is -2, because a negative times a negative is a positive, so -2 times -2 is also 4. Squaring throws away the sign. It treats a number and its opposite exactly alike, folding them together into the same result. And so, when you try to walk backward through a square, to undo it, the path splits in two. There were two roads in, and so there are two roads out. This is why a quadratic so often has a pair of answers, a positive possibility and a negative one. Twins born from the folding of the square. How do you actually solve one? There are a few ways, and they are worth feeling, because each one shows you something different about the shape of the problem. The oldest and most beautiful way is the very method al-khwarizmi used, and it has a name that tells you exactly what it is. It is called completing the square. And it is not just a phrase. It is a literal action, a piece of geometry made of imagined tiles. Picture the squared unknown as an actual square tile, whose side is the unknown length. Now picture the plain unknown term, the part where the unknown appears just once, as a long, thin strip attached to one side of that square. You have a square with a strip stuck onto it, an awkward L sort of shape, or a square with a flap. The trick, the whole insight, is this. You take that strip and you cut it in half lengthwise, and you move one half around to a second side of the square, so now the square has a strip along its bottom and a strip up its side, of equal width. And when you look at that shape, you can see that it is almost a bigger square. It is a bigger square with just one small corner piece missing, a little square notch at the outer corner. So you complete it. You add in that missing corner piece, and the moment you add the corner, the whole shape becomes a perfect, complete, larger square, whose area you can easily describe, and whose side you can therefore find by taking a square root. That is completing the square. It is not a trick at all. It is carpentry. It is rearranging tiles until the shape becomes a clean square that you can measure. 1200 years ago in Baghdad, this was drawn out with real diagrams, and it is still, underneath all the modern symbols, exactly what we do today. If you take that geometric act of completing the square, and you do it not with specific numbers but in full generality, using letters for all the knowns the way Viet taught us, then something remarkable falls out. You get a single master recipe that solves every quadratic equation there has ever been or ever will be, in one stroke, no matter what its numbers are. This master recipe is so important that it is given a special name, the quadratic formula, and generations of students have memorized it, often without ever being told that it is simply completing the square, done once in general, and remembered so that no one has to redo the carpentry every time. The formula takes the three numbers that define any quadratic, the amount of the squared term, the amount of the plane term, and the lone constant, and it combines them in a fixed way, involving a square root, to hand you both answers at once. I will not draw it out as a line of symbols, because as symbols it looks forbidding, and you are trying to sleep, not to study for an exam. But I want you to feel what it is. It is the genie that al-Khwarizmi's careful work was reaching toward. It is the general solution, the recipe freed from any particular numbers, the thing the ancient world could never write down because it had no language for the general. It is a small monument to the whole journey we have traveled tonight. There is one part of that master recipe that deserves its own quiet moment, because it is genuinely lovely. Buried inside the formula is a smaller quantity, formed from the three numbers of the quadratic, that sits underneath a square root. This little quantity acts as a kind of weather forecast for the whole equation, telling you in advance what sort of answers to expect, before you do any of the hard work. If that quantity comes out positive, the equation has two distinct real answers, two separate solutions, as we discussed, the twins. If it comes out exactly zero, the two twins have merged into one, and there is a single answer, sitting where the two would have been if they had not collapsed together. And if that quantity comes out negative, then something interesting happens. You are asked to take the square root of a negative number, and we already met that ghost tonight, in the story of the Italian cubic. It means there are no ordinary real answers at all. The solutions have stepped sideways into the world of those imaginary numbers, the ones that turned out to be so useful in physics. So this one small quantity, often called the discriminant, because it discriminates between the cases, lets you peer at a quadratic and know its fate at a glance. 2 answers, 1 answer, or none of the ordinary kind. It is a little oracle, hidden in the heart of the formula. So now you have the 2 great pillars of basic algebra standing in your mind. The linear equation, where the unknown stands alone, solved by patient balance tidying, with 1 answer, and the quadratic equation, where the unknown is squared, solved by completing the square or by the master formula, with its pair of answers and its little oracle of a discriminant. Almost everything else in algebra is built outward from these 2. And the next natural question, the one that pulls us into the wider landscape, is simple. What happens when the unknown is raised to even higher powers? What happens when it is multiplied by itself not once, to make a square, and not twice, to make a cube, but again and again? This is where algebra begins to open out into a much larger country, and where we begin the part of tonight that explores the branches and extensions of the core idea. When you allow the unknown to be raised to higher and higher powers, and you add together several such terms, each with its own power and its own number in front, you get something called a polynomial. The word looks intimidating, but it simply means many terms. A polynomial is a sum of pieces, where each piece is some number multiplied by the unknown raised to a whole number power, the powers stepping down like a staircase, from the highest, down through the square, down to the plain unknown, and finally to a lone number with no unknown at all. The highest power in the staircase is called the degree of the polynomial, and it turns out to be enormously important, because it quietly controls the personality of the whole thing. A polynomial of degree 1 is just our linear equation, the line. A polynomial of degree 2 is the quadratic, the squared one, with its pair of answers. A polynomial of degree 3 is the cubic, the one the Italians fought over, and it can have up to 3 answers. Degree 4, the quartic, which Cardano's student Ferrari conquered, can have up to 4. And in general, a wonderful pattern holds. The degree tells you the maximum number of answers the equation can have. A polynomial reaches into the number line and can touch it in at most as many places as its degree. The staircase of powers becomes a staircase of possible solutions. This pattern, that the number of solutions matches the degree, was felt for a long time before it was fully proven, and proving it properly, including the imaginary solutions as well as the ordinary real ones, became one of the cornerstones of the subject, sometimes called the fundamental theorem of algebra. It says in spirit that if you are willing to include those ghostly imaginary numbers among your solutions, then a polynomial always has exactly as many solutions as its degree, no more and no less, every time, with perfect reliability. The young German mathematician Carl Friedrich Gauss, one of the greatest who ever lived, gave a proof of this around the year 1800 as a very young man and returned to it again and again across his life, polishing it. There is something deeply restful in that theorem, if you sit with it. It says the universe of polynomials is orderly. Nothing is missing, nothing overflows. Every equation has exactly its proper number of answers, no surprises, no gaps, as long as you are generous enough to count the imaginary ones. A quiet law of completeness, holding the whole world of equations gently in place. Before we lift up into that wider country, though, let us spend a gentle while with the small, everyday machinery, the actual handling of these expressions, because there are a few quiet rules at work whenever anyone does algebra, and they are restful to understand, and you have almost certainly used them without ever being told their names. They are the hidden good manners of the subject, the things the symbols are always quietly obeying. The deepest of these, the one that everything else leans on, is a rule about how adding and multiplying get along with each other. On their own, adding and multiplying are two different acts, but they are not strangers. They are bound together by a single agreement, and that agreement is the secret handshake at the heart of all algebra. Picture it this way. Suppose you have some quantity, and you want to multiply it by a sum of two other things added together. You could first add the two things, and then multiply the result by your quantity. Or you could multiply your quantity by each of the two things separately, and then add those two results together at the end. The agreement says that both roads arrive at exactly the same place. It does not matter whether you add first and then multiply, or multiply each piece and then add. The answer is the same either way. This is called the distributive law, because the multiplying distributes itself across the addition, reaching in and touching each piece. There is a picture for it, simple and physical, that makes it feel obvious rather than abstract. Imagine a rectangle of garden with a certain height and a width made of two parts side by side, a wider part and a narrower part. The whole area of the garden is its height times its full width. But you can also see the garden as two smaller rectangles standing next to each other, the height times the wider part, plus the height times the narrower part. It is plainly the same patch of ground, measured two ways. The height has been distributed across the two pieces of the width. That is the whole law, drawn in soil. And once you feel it, you can see that this single agreement is what lets you take an expression where things are bundled inside brackets and multiply them out, opening the brackets, reaching the multiplier in to touch each term. Whenever you have seen brackets in algebra be opened up and spread out into a longer expression, this quiet law was doing the work. It is, by the way, exactly the rule that bound addition and multiplication together in those abstract structures called rings, that we will meet a little later, the structures where you can both add and multiply. So this gentle agreement about a garden is also one of the deep girders holding up the most abstract algebra there is. The small machinery and the grand structures are the same machinery, only seen from different distances. Now, that opening of brackets, the spreading out, can also be run backward, and running it backward is one of the most useful skills in all of algebra. It is called factoring, and it is the art of looking at a spread-out expression and finding the hidden multiplied pieces folded inside it. If multiplying out is opening a flower, factoring is folding it back into the bud. You look at a long expression and you ask, what simpler things, multiplied together, would have produced this? And when you can answer that, when you can find the pieces that multiply to give the whole, you gain something quietly powerful, because of one beautiful fact about multiplication and zero. If several things multiplied together give zero, then at least one of those things must itself be zero. There is no other way to multiply your way to nothing. Two numbers, neither of them zero, can never multiply to give zero. So if you can take an equation that equals zero and factor the side with the unknown into multiplied pieces, then you know that the answer must be whatever makes one of those pieces equal to zero. You have broken one hard question into a few easy ones. This is, underneath the modern symbols, one of the main ways quadratics and higher equations are solved by hand, by folding them into multiplied pieces and then asking, gently, what would make each piece vanish? Factoring is the patient art of finding the seams in a thing, the natural places where it comes apart. There is one more piece of everyday machinery worth resting on, and it concerns those little raised numbers, the powers, the exponents, that tell you how many times something is multiplied by itself. We have used them all night, the squared and the cubed and beyond. On the surface they are simple, just a shorthand for repeated multiplication, a small number perched up high counting the copies. But they hide a lovely logic, and following that logic leads somewhere unexpected and quietly profound. Start with the obvious. When you multiply a quantity by itself a certain number of times, and then multiply that by the same quantity a few more times, the total number of copies is just the two counts added together. 3 copies multiplied by 2 more copies makes 5 copies in all. So multiplying powers of the same thing turns into adding their little raised numbers. Multiplication on the ground floor becomes addition up in the attic. That is the basic rule, and it is the very thing that Napier's logarithms, which we spoke of earlier, were built to harness, the turning of hard multiplication into easy addition. But here is where it becomes beautiful. That rule, that multiplying powers means adding their exponents, is so clean and so dependable that mathematicians decided to let it be the guide, to follow it even past the place where the original picture made sense. Repeated multiplication only really means something for whole numbers of copies. You can multiply a thing by itself 3 times, but what could it possibly mean to multiply a thing by itself 0 times, or a negative number of times, or half a time? These have no meaning in the original picture. There is no such thing as half a copy. And yet, rather than throw these cases away, mathematicians asked a gentler question. If these strange powers were to exist, what would they have to be in order to keep the lovely rule unbroken, in order to keep multiplying meaning adding? And the answers fall out on their own, forced into place by the demand that the pattern hold. To raise something to the power of 0 must give 1, always, because that is the only value that keeps the bookkeeping consistent. The only way the steps continue to line up as you walk the powers downward. A negative power must mean 1 divided by the ordinary power, the reciprocal, the flipping over, because that is what makes the adding of exponents keep working when one of them dips below 0. And a fractional power, a power of 1/2, must mean the square root, the thing that multiplied by itself gives back the original, because 2 halves added together make 1 whole, so the half power, used twice, must rebuild the first power. Each of these strange new powers is summoned into existence not by a picture, but by the insistence that a pattern remain whole. And notice, gently, that this is the very same move we will see again tonight, with the numbers themselves, the move of growing a definition outward, past where it first made sense, in order to keep a beautiful pattern unbroken. It is one of the deepest habits of mathematics, this faithfulness to pattern, this willingness to follow a rule into new territory, and let it tell you what the new territory must contain. So the small machinery turns out to carry the same spirit as the grand ideas. The distributive handshake, binding, adding to multiplying, the folding and unfolding of factoring, the powers that grow their own meaning to keep a pattern alive. None of these are arbitrary rules to be memorized in fear. Each one is a small piece of sense, a quiet agreement that makes the whole structure hang together. And hidden inside the powers, inside the way sums raised to powers spread themselves out, there lives one of the most elegant patterns in all of mathematics, a simple triangle of numbers that appeared independently in China, in Persia, in India, and in Europe, each time discovered by people who had never heard of one another. It is worth resting your mind on that triangle for a while, in the quiet, before we rise up into the wider country of curves and shapes. If you take a simple sum of 2 things, and you multiply that whole sum by itself, again and again, raising it to higher and higher powers, the results spread out into longer and longer expressions, and the numbers that appear in front of each piece follow a pattern of breathtaking regularity. Raise the sum to the first power, and there is nothing much to see. Raise it to the second, the squared, and 3 terms appear, with a 1, a 2, and a 1 standing in front of them. Raise it to the third power, and you get 4 terms, with a 1, a 3, and a 1. To the fourth power, 5 terms, with a 1, a 4, a 6, a 4, and a 1. Write these rows of numbers down, one beneath the other, each row a little longer than the last, and center them, and they form a triangle, widening as it descends, a 1 at the very top, and the rows blossoming outward below. And this triangle has a property so simple a child can use it, and so deep that mathematicians still draw meaning from it. Every number inside it is simply the sum of the 2 numbers resting just above it, to its left and to its right. That is the only rule you need. Begin with a 1 at the top, put 1s down both edges, and fill every inner space with the sum of the 2 numbers above it. The whole infinite triangle grows itself from that single gentle instruction, each number cradled by the 2 above, like a stone supported by 2 stones beneath it in an arch. This triangle was found, as I said, in many places, by many hands. In China it is remembered as the triangle of Yang Hui, a mathematician of the 13th century, though it was known there even earlier, used as a tool for extracting roots. In the Persian world it was studied by al-khwarizmi and by the poet Omar Khayyam, whom we met tonight in his work on the cubic, and in Iran it is still sometimes called Khayyam's triangle. In India its rows had been described, in connection with the patterns of poetry and rhythm since ancient times. And in Europe it took the name of the French thinker Blaise Pascal, who studied it deeply in the 1600s, not for powers at all, but because it turned out to answer a completely different question, a question about chance and gambling, because the very same numbers in this triangle also count something else entirely. They count the number of different ways you can choose a handful of things from a larger group. How many ways to choose 2 children from a class, or 3 cards from a hand, or 5 people from a crowd? The answer is always sitting there, waiting, in the right row of the triangle. And from counting the ways things can be chosen, it is a short step to the mathematics of probability, to working out the odds of how many heads might come up in a row of coin flips, which is exactly the gambling question Pascal was wrestling with. So this one quiet triangle, grown from the simplest rule of adding 2 numbers above, ties together the raising of sums to powers, the counting of combinations, and the laws of chance. 3 rooms of mathematics that look quite separate, all connected by the same little staircase of numbers. And if you trace certain gentle diagonal paths across it, adding the numbers you pass, you find, hidden in the slopes, the famous sequence of Fibonacci, the very numbers from the merchant's book that began the European chapter of our story, each one the sum of the 2 before it, appearing unbidden in the folds of the triangle. There are few things in mathematics as restful to contemplate as this, a shape of pure simplicity that quietly contains so much, asking nothing of you but that you notice it. And speaking of sequences, of numbers that follow one after another in a pattern, let us rest a moment longer on those, because they are among the gentlest things in all of algebra, and they hold a small wonder of their own. A sequence is just a list of numbers marching along according to some rule. The simplest kind grows by adding the same amount at each step, like a staircase with even risers, 1, then 4, then 7, then 10, always stepping up by 3. These steady marching sequences are called arithmetic, and there is a lovely old story about them, concerning the same German mathematician, Gauss, whom we met proving the completeness of the equations. As the story goes, when he was a very young boy in school, his teacher, wanting a long while of quiet, told the class to add up all the numbers from 1 to 100, expecting it to take the whole hour. The young Gauss thought for a moment and wrote down the answer almost at once. He had seen something. He saw that if you pair the numbers cleverly, the first with the last, the one with the 100, they sum to 101, and the second with the second to last, the 2 with the 99, also sum to 101, and so on, all the way in, every pair making the same 101. There are 50 such pairs, and so the whole sum is 50 times 101, which he could work out in a breath. A long, dreary task collapsed into a single easy multiplication, because he had found the hidden symmetry in the list, the way it folds onto itself from both ends. That trick is the whole secret of adding up any steadily marching sequence, and it is the kind of thing that, once seen, can never be unseen. The other simple kind of sequence grows not by adding the same amount each time, but by multiplying by the same amount each time, and these are called geometric. Start with 1, and keep halving, and you get 1, then a half, then a quarter, then an eighth, each step half the size of the one before, the numbers shrinking toward nothing but never quite reaching it. And here lives one of the gentlest small paradoxes in all of mathematics, a thing worth holding as you drift. If you add up such a shrinking sequence, all of it, every single one of those endlessly halving pieces, all the way out to infinity, you might expect the total to be infinite too, since you are adding up endlessly many things. But it is not. The total is finite. The endless sum of a half, plus a quarter, plus an eighth, plus a 16th, and onward forever, comes to exactly 1. The whole infinite staircase of shrinking steps fits, in the end, inside a single unit, leaving no gap and no overflow. You can almost feel why if you picture it. Imagine standing at a wall and stepping half the remaining distance toward it, and then half of what is left, and half again, forever. You take infinitely many steps, and yet you never pass the wall, and the total distance you cover is exactly the distance to the wall, and not one bit more. Infinitely many things, adding up to something finite and whole. There is something deeply restful in that idea, the notion that an endless process can have a calm and definite ending, that infinity can be held, gently, inside a bounded space. It is the kind of thought that the mind can sink into and follow down towards sleep, the steps growing smaller and smaller and smaller, halving and halving, never quite arriving, and yet somehow, in the end, complete. So now, with the small machinery understood, and the triangle and the sequences resting quietly in your mind, we can finally lift up into the widest and most beautiful country of all, the one I have promised you twice now. Now we come to the deepest extension of all, the one Descartes gave us, the one I promised we would return to. So far, we have talked about equations as things to be solved, as balances to be tidied until the unknown stands alone. But there is another way to look at an equation, and it changes everything about how we see the subject. Instead of asking, what one value makes this true, you can let the unknown roam freely across all possible values, and ask, what does the whole family of results look like, as the unknown slides up and down? And when you do that, you can draw a picture. This is the marriage of algebra and geometry, and it is one of the most beautiful ideas in all of human thought. Here is how the marriage works. Imagine a flat sheet, and on it draw two lines crossing at right angles, like the corner of a window frame, one running left to right, the other running up and down. Every point on that sheet can now be named by two numbers, how far across it is, and how far up it is. This is the coordinate plane, and the idea of naming points by pairs of numbers is exactly what Descartes gave us, which is why we still call these Cartesian coordinates, from the Latin form of his name. Now take an equation that links two quantities, an x and a y, where for every value of the across number, the equation tells you a matching value for the up number. Each such pair is a point on the sheet, and as you let the across number slide smoothly through all its values, the matching points trace out a shape, a curve, drawn in the air of the plane. The equation, which was a string of symbols, becomes a line or a curve you can actually see. Algebra becomes a picture. Geometry becomes an equation. The two great branches of mathematics, which had grown up almost separately for 2,000 years, turned out to be two languages describing one single landscape. And now that earlier promise comes due, the reason a simple equation with no squared term is called linear. Because when you draw such an equation on the coordinate plane, letting the unknown roam, the picture you get is a perfectly straight line. That is the whole reason for the name. Linear, from line. The simplest equations make the simplest pictures, straight and unbending. And the quadratic, the squared equation, when you draw it, makes a graceful sweeping curve called a parabola, the same shape as the path of a thrown ball, or the curve of a satellite dish, or the cables of certain bridges. And now you can see, with your own eyes, why a quadratic has two answers, or one, or none. The answers are the places where its curve crosses the across line, the horizontal. A parabola, that smooth valley shape, can cross a horizontal line in two places, dipping down through it and rising back up. Or it can just kiss it at the very bottom, touching in one place. Or it can hover entirely above and never touch at all, which is the case with no real answers, the case of the negative discriminant. The little oracle we spoke of earlier is now something you can see. The whole hidden behavior of the equation is laid out as a shape on a sheet. This is what Descartes opened up. He let us see algebra, and once you can see it, 1,000 new questions become askable, because now you can talk about where curves rise and fall, where they cross, where they reach their highest and lowest points, how steeply they climb. A vast new country opened from this single idea, and most of the mathematics that powers the modern world is built in that country, on the ground Descartes laid, where every equation has a shape, and every shape has an equation. Out of this marriage of algebra and geometry grew one more idea, perhaps the most useful single idea in all of modern mathematics, and it is called the function. A function is a beautifully simple thing once you feel it. It is a rule that takes something in and gives something back, reliably, the same way every time. You can picture it as a little machine with a slot at the top and a chute at the bottom. You drop a number into the slot, the machine does its fixed work, and a number comes out the chute. Drop in the same number tomorrow, and the very same number comes out, because the rule does not change. That dependable, one-in, one-out behavior is the whole of it. A function is a faithful machine. You give it an input, it returns exactly one output, with no wavering. The squaring rule is a function. Feed it 3, it returns 9. Feed it 5, it returns 25. Feed it 3 again, and it returns 9 again, forever. Each input has exactly one partner waiting for it on the other side. The reason functions matter so much is that almost everything in the world that depends on something else can be described as a function. The distance a car has traveled depends on how long it has been driving. So distance is a function of time. The amount of interest your savings earn depends on how much you have saved. The brightness of a screen depends on the setting of a dial. The position of a planet depends on the moment you choose to look. Wherever one thing depends upon another, in a steady, rule-following way, there is a function quietly describing the relationship. And because every function can be drawn as a shape on the coordinate plane, that smooth sheet with the across and the up directions, you can see the relationship as a picture. You can watch the line of a steady journey climb evenly across the page. You can watch the curve of growing savings bend gently upward, faster and faster. The function turns a relationship into a shape, and the shape lets you understand the relationship at a glance, where it rises, where it falls, where it is fastest, where it rests. This single idea, the function, became the basic vocabulary of all the sciences. When a physicist describes how an object falls, or a biologist describes how a population grows, or an engineer describes how a signal travels along a wire, they are writing down functions, machines of dependence, each one a rule linking one quantity to another. Algebra gave the world this vocabulary, and the world has been speaking it ever since. Now let us add one more layer, gently, because it appears everywhere, and it is not hard to feel. So far we have mostly had a single unknown to find, but often life gives you more than one unknown at the same time, two quantities you do not know, tangled together. And to pin them both down, a single equation is not enough. With two unknowns and only one equation, there are endlessly many possibilities, because the two unknowns can trade off against each other in countless ways. But if you have two separate true statements about the same two unknowns, two equations that must both hold at once, then suddenly the possibilities narrow, often down to a single answer, one pair of values that satisfies both equations together. This is called a system of equations, several equations sharing the same unknowns, all required to be true at the same moment. And there is a lovely picture for it. Remember that each equation in two unknowns draws a line or a curve on the coordinate plane. If you must satisfy two equations at once, you are looking for a point that lies on both shapes at the same time, which is exactly the place where the two shapes cross. The solution to a system of equations is a crossing point. Where the two lines meet, there sit the two values that make both statements true together. To solve such a system, you can again lean on that same faithful idea of balance, combining the equations cleverly, adding or subtracting them so that one of the unknowns cancels away and vanishes, leaving you with a single equation in a single unknown, which you already know how to handle. It is the old balancing trick, al-muqabala, the cancelling of equal things, used now to make one of two unknowns quietly disappear. These crossing points, these solutions to systems, are not abstract at all. They are everywhere in the practical world. When an economist asks at what price the amount people want to buy exactly matches the amount sellers want to sell, that balancing price is the crossing point of two relationships, found by solving a system. When an engineer balances the forces in a bridge, with many beams pushing and pulling on one another, they are solving a great system of equations, sometimes with hundreds or thousands of unknowns at once, all required to balance together. And when your phone works out where you are standing tonight, from the signals of distant satellites, it is solving a system of equations to find the one location that fits all the signals at once, the single crossing point of several invisible spheres. But we are getting ahead of ourselves, toward the part of tonight where we look at where all this lives in the world around you. Before that, there is one more turn in the story of algebra itself, the strangest and most abstract turn of all, and the one that takes us to the edge of the deepest questions. So let us follow the idea upward, into the clouds, where algebra stopped being about numbers at all and became about something larger. For most of its history, across all the centuries we have traveled tonight, algebra was the art of finding unknown numbers. From the Babylonian fields to Descartes' curves, the goal was always a number, hidden, then revealed. But in the 1800s, mathematicians made a leap so bold that it changed the meaning of the word algebra itself. They began to ask a different kind of question. Instead of asking what number solves this equation, they began to ask, what are the rules of the game itself, and what other games follow the same rules? They turned their attention away from the numbers and toward the operations, the very acts of adding and multiplying and combining. They asked, what is it that makes addition behave the way it does? What deep properties does it have? And are there other things in the world, not numbers at all, that combine according to those same deep properties? This shift, from studying numbers to studying the structure of operations, is the birth of what we now call abstract algebra, or modern algebra, and it is one of the great achievements of the human mind. Let me try to give you a feel for it, slowly. Think about the simple act of adding whole numbers. It has certain quiet properties that you have always known but perhaps never named. There is a number that does nothing when you add it, namely 0. Add 0 to anything and it stays the same. Mathematicians call such a do-nothing element an identity. Every number also has a partner that cancels it back to 0, its negative, so that a number and its partner together undo each other and return you to the do-nothing 0. These partners are called inverses, and it does not matter how you group the additions when you add three numbers together, you get the same total whichever pair you add first. When a collection of things, together with a way of combining them, has all of these gentle properties, a do-nothing element, a partner for everything that cancels it, and that freedom in how you group things, mathematicians call the whole structure a group. And the astonishing thing, the thing that opened a new world, is that groups are everywhere, and most of them have nothing to do with numbers at all. Here is the example that brings it to life, and it is something you can hold in your hands in the dark. Think of a square, a simple square tile. Now think of all the ways you can pick it up, turn it, and set it back down, so that it lands in exactly the same outline, looking unchanged. You can rotate it a quarter turn, and it fits its own outline perfectly. You can rotate it a half turn, or 3/4, or leave it alone entirely. You can also flip it over across various lines, and it still lands in the same square outline. All of these moves, these turnings and flippings that leave the square looking the same, are called its symmetries. And here is the quiet miracle. These symmetries, these physical motions of a square, combine according to exactly the same deep rules as addition of numbers. Doing one motion and then another is like combining two elements. There is a do-nothing motion, leaving the square alone, which acts just like 0. Every motion has another motion that undoes it, just like a number and its negative, and the grouping freedom holds as well. The symmetries of a square form a group in precisely the same sense that the numbers do. So a structure first noticed in arithmetic turns out to live also in the turning of a tile, in the patterns of a tiled floor, in the facets of a crystal, in the arrangement of petals on a flower, in the deep symmetries of the laws of physics themselves. Algebra had found a way to talk about symmetry, about structure, about the very idea of things that can be combined and undone. It had risen above number entirely, into a description of pattern itself. And this rise into the clouds was not done for its own sake. It was driven by one specific, burning question, a question left over from everything we have discussed tonight, and the answer to it is one of the most poignant and beautiful stories in all of mathematics. So let us turn to that question now, because it brings together the Italian feuds over the cubic, the master formula for the quadratic, and these strange new groups of symmetries, all into a single thread. And it carries within it two young men who died far too soon, one of whom was born in the country where you may be lying tonight. The question was this: we have a master formula for the quadratic, the squared equation, a clean recipe using square roots that always gives the answer. After much struggle and secrecy, the Italians of the Renaissance found master formulas for the cubic and the quartic too, the third and fourth degrees, more complicated, using cube roots as well as square roots, but still clean recipes built only out of the ordinary arithmetic operations and the taking of roots. So a natural and powerful expectation took hold. Surely, the pattern continues, surely there is a master formula for the fifth degree equation, the quintic, and for every degree beyond, if only someone clever enough could find it. For nearly 300 years, the finest mathematicians searched for the formula for the quintic. They searched, and they searched, and they failed. Always they failed. And slowly, a strange suspicion began to grow. What if the reason no one could find the formula was not that it was hard to find, but that it did not exist at all? What if, for the fifth degree and beyond, there simply is no master formula of that kind, no recipe built out of ordinary arithmetic and roots that can solve every such equation? That would be a very different sort of claim. It is one thing to fail to find something. It is another thing entirely to prove that the thing cannot exist, that the search was doomed from the start. And proving that something is impossible is one of the hardest and deepest things a mathematician can ever do. The man who proved it was a young Norwegian named Niels Henrik Abel. He was born in 1802 in a poor family, in a country at the very edge of Europe, far from the great centers of learning. His father died when he was young, leaving the family in hardship, and Abel grew up with very little. But his mathematical gift was so blazing and so unmistakable that his teachers and a few kind patrons scraped together what they could to support him. And while still in his early 20s, working largely alone, Abel did what 3 centuries of the greatest minds in Europe had failed to do. He proved, rigorously and finally, that there is no general formula, built out of ordinary arithmetic and the taking of roots, that can solve every equation of the fifth degree. The search that had consumed mathematics for 300 years was over, not with a discovery, but with a proof of impossibility. The door everyone had been trying to open was shown, once and for all, to be a painted wall. It is a result of enormous depth, and it carries a quiet ache, because it tells us there is a real and permanent limit to a certain kind of hope. Abel himself lived in poverty and struggled for recognition. He traveled across Europe seeking a position worthy of his gift and was repeatedly overlooked. And in 1829, at the age of just 26, he died of tuberculosis, cold and poor, before the letter arrived offering him the professorship he had long deserved. The letter reached his country 2 days after his death. Norway remembers him now as one of its greatest minds, and there is a prize given in his name today that stands among the highest honors in all of mathematics, a small and belated act of justice for a young man who gave so much and received so little in his short life. But Abel had shown only that no single formula could solve every quintic. He had not fully explained why some specific equations could still be solved and others could not, what exactly separated the solvable from the unsolvable. That final, deepest piece came from another young man, a Frenchman named Évariste Galois, whose life was even shorter and even more tragic, and whose ideas were even more profound. Galois realized that the secret to whether an equation can be solved by a formula lies not in the equation itself, but in the symmetries of its solutions, in the hidden group structure connecting its answers to one another. He saw that to each equation there belongs a group, a structure of symmetry exactly like the symmetries of the square we spoke of, and that the shape of this group decides everything. If the group has a certain gentle, layered structure, the equation can be solved by a formula. If the group is too tangled, too richly knotted in its symmetry, then no formula can ever exist, and that is precisely what goes wrong at the fifth degree. The answer to a 300-year-old question turned out to live in the realm of pure symmetry. Galois wrote these ideas down in a frantic rush, because he knew his time was short. He was a fierce and political young man, caught up in the turmoil of his age, and at the age of just 20, in 1832, he was killed in a duel, the reasons for which remain murky to this day. The night before the duel, fearing death, he sat up writing out his mathematical ideas in a long letter to a friend, scribbling in the margins, racing against the dawn, begging that his work be shown to the great mathematicians of the day so that it would not be lost. He died the next morning. His ideas, nearly lost, were eventually understood, and they reshaped the whole of mathematics. The field that grew from that desperate midnight letter, the study of these groups of symmetry, is now one of the central pillars of the subject, and it reaches into physics, into chemistry, into the deepest descriptions of reality we possess. Two young men, then, one Norwegian and one French, both dead before the age of 30, together closed the question that the Italian masters had opened, and in doing so, they lifted algebra into a new and higher form, the study not of numbers, but of structure and symmetry itself. Once mathematicians had learned to study structure rather than mere numbers, the door opened to a whole family of related structures, each one a collection of things with rules for combining them, each one a kind of game with its own logic. The group, which we have met, is the simplest. Above it sit richer structures with names like rings and fields, and you do not need to hold the details, only the spirit. A ring is a structure where you can both add and multiply, the way ordinary numbers let you do both. A field is a ring that is even more generous, where you can divide as well, where almost everything has a partner that undoes multiplication, the way 3 has a partner, a third, that brings it back to 1. The ordinary numbers you have always known form a field, but so do other, stranger collections, including small, finite worlds of numbers that wrap around like the hours on a clock, where after the highest number, you loop back to the beginning. On a clock, 7 hours after 8 is not 15, it is 3, because the numbers wrap. These wrapping number worlds are fields too, and they turn out to be the secret engines behind the codes that protect your messages and your money, as we will come to shortly. The point, the restful and beautiful point, is that algebra had become the study of all possible arithmetics, all the different ways that things can be combined and undone, not just the one arithmetic we happen to grow up with. It became a vast catalogue of imaginable worlds, each with its own consistent rules, and mathematicians could wander among them, study their shapes, and find again and again that these abstract worlds matched something real out in the universe. One branch of this wider algebra deserves special attention tonight, because more than any other, it is the form of algebra that runs the modern world, humming underneath nearly every screen and every calculation. It is called linear algebra, and it grew from a simple need, the need to handle many equations and many unknowns all at once. Not 2 or 3, but dozens, hundreds, thousands, even millions. When you have a great many linear equations, all sharing a great many unknowns, writing them out one by one becomes hopeless. So mathematicians invented a way to gather all the numbers of such a system into a neat rectangular grid, a block of numbers arranged in rows and columns, and they called this grid a matrix. A matrix is just an organized table of numbers, but treating that whole table as a single object, something you can work with all at once, turned out to be one of the most powerful ideas in applied mathematics. You can add 2 such grids, and even multiply them together by a particular rule, and when you do, the grid stops being a passive table and becomes something active. It becomes a transformation, a machine that takes points in space and moves them, stretches them, rotates them, shears them into new positions. This is the heart of why linear algebra runs the visual world. Every time a shape turns on a screen, every time a video game world rotates around you, every time a photograph is scaled or skewed, a matrix is quietly doing the work, taking the coordinates of every point and transforming them all together in one sweep. The little arrows that describe positions and directions in space are called vectors, simply ordered lists of numbers, and a matrix is the machine that acts on those arrows, sending them to new places according to a fixed rule. Combine two transformations, one after the other, and the combined effect is captured by multiplying their matrices together. So the strange multiplication rule for these grids is not arbitrary at all. It is exactly what is needed to capture the doing of one transformation followed by another. The very same idea of combining motions that we met in the symmetries of the square. Underneath the surface, it is all the same music. Things that can be combined, and the structure of how they combine. Within linear algebra there lives one idea so useful that it is worth meeting gently, even half asleep, because it powers things you touch every day. Imagine a transformation that stretches and rotates space in some complicated way. Most arrows, when this transformation acts on them, get knocked off in a new direction, pointing somewhere quite different from where they started. But for almost any such transformation, there are a few special directions, a few special arrows, that do not get knocked askew. When the transformation acts on them, they keep pointing exactly the same way as before, only stretched longer or squashed shorter along their own line. These unmoved directions, these arrows that hold their heading through the whole upheaval, are called the special directions of the transformation, and the amount each one is stretched is its own particular number. This may sound abstract, but those special directions are quietly everywhere. They are how engineers find the natural ways a bridge or a building likes to sway and vibrate, so they can keep those sways from matching an earthquake and growing dangerous. They are how a search engine first learned to rank the entire web, by finding the special direction of an enormous matrix describing how every page links to every other, a calculation across billions of pages that comes down to this one idea. They are how a photograph or a song can be squeezed down into a smaller file, by keeping only the most important special directions and gently discarding the rest. And they sit at the very foundation of quantum physics, where the special numbers of certain transformations turn out to be the only values a measurement can ever return. So this one quiet idea of directions that hold their heading while everything around them turns, reaches from a swaying bridge to a search engine to the deepest layer of physical reality. That is the reach of linear algebra. It is the algebra of many things at once, of space itself, and it is the form of the subject that, more than any other, makes the machines around you work. And this brings us, at last, gently, out of the world of pure ideas and back into the room where you are lying. Because all of this, the unknowns and the equations and the balancing, the curves on the plane, the groups of symmetry, the grids that transform space, is not locked away in textbooks. It is alive, right now, all around you, working silently while you rest. So let us spend a little while simply noticing where algebra is living tonight, in the things within your reach, in your own body, in the building that holds you, in the sky beyond your ceiling. Let us see how the oldest idea we have followed, the hidden number found by the rules it obeys, is at work in the dark around you this very moment. Begin with the device that is speaking to you. We started tonight by saying it was solving equations to turn stored numbers back into a voice, and now you can feel what that means. The sound of these words was once a wave in the air, rising and falling. To store it, that wave was measured tens of thousands of times every second, each measurement a number. To play it back, the device must take those numbers and reconstruct the smooth wave between them, working out the values in the gaps, which is the solving of equations, over and over, faster than thought. And to do it without the file being impossibly large, the sound was compressed, squeezed down using the very ideas of linear algebra we just met, keeping the important directions and letting the rest go. Every song you have ever streamed, every voice you have ever heard through a speaker, reached you through algebra, through the finding of unknowns and the transforming of grids of numbers. Now think of how that same device knows where it is. If you have ever watched a little dot find your position on a map, You have watched algebra solve a system of equations in real time. High above you, satellites are circling, each one broadcasting a steady signal that says, in effect, here is who I am, and here is the exact time I sent this. Your device listens to several of them at once. From the tiny delay in each signal, it works out how far it is from each satellite, and each distance places it somewhere on an invisible sphere around that satellite. One sphere is not enough. 2 spheres narrow you to a circle where they overlap, but with several spheres at once, there is only one point in all of space that lies on every one of them together, and that single crossing point is where you are standing. Finding it is solving a system of equations, the exact idea we met as the crossing of curves on Descartes' plane, now lifted into 3 dimensions and solved many times a second, so the little dot can follow you as you move. The whole sky has become a coordinate system, and your place within it is the solution to an equation. Think next of the messages you send and the money you move, all of which travel safely only because of algebra, and specifically because of those strange wrapping number worlds, the clock-like fields we mentioned. When you buy something or send a private message, the information is scrambled using a kind of mathematical lock built out of arithmetic that wraps around. Arithmetic where multiplying large numbers together is easy, but pulling them back apart is so monstrously hard that not even the fastest machines on Earth can do it in any reasonable time. The security of nearly everything you do online rests on this strange imbalance, a piece of pure algebra in those finite number worlds, easy to do in one direction, practically impossible to undo in the other, unless you hold the secret key. Every padlock icon you have ever glanced at is algebra standing guard. Even the reliability of all this, the fact that a file arrives whole and a message arrives uncorrupted across a noisy world, rests on algebra. Information is bundled together with cleverly chosen extra numbers, redundancy built from polynomials and from those wrapping number worlds, so that if some of the data is scrambled along the way, the missing or broken pieces can be worked out and restored from what survived. It is the finding of unknowns again, the recovery of lost values from the rules they must obey. The same idea lets a scratched disk still play and lets a faint signal from a spacecraft billions of miles away arrive on Earth and be pieced back together, perfect, despite all the noise of the void it crossed. And it is not only your machines. It is your own body lying here in the dark. The dose of any medicine you have ever taken was worked out with equations describing how a substance spreads through the body and fades over time, so that the amount is enough to help and not enough to harm, a balance found by solving for an unknown. If you have ever had an image taken of your insides, a scan that builds a picture of a slice through your body without ever cutting it open, that picture was assembled by solving an enormous system of equations, reconstructing the hidden interior from many measurements taken around the outside, the unknown densities of your own tissues found by the rules the measurements obeyed. The building around you was held up by equations too, the loads and forces in every beam and column balanced by engineers solving great systems so that the structure stands quietly through the night without a thought. The temperature settling evenly through your room, the water that reached your tap at the right pressure, the electricity flowing at a steady voltage to the lamp you switched off. All of these were designed and are governed by relationships written in the language of algebra, unknowns balanced against knowns, quantities held in their proper proportion. You are lying inside a quiet machine of solved equations, and it is holding you safely, and you never have to think about any of it. There are gentler places it lives too, places you might not expect. If you have ever heard music tonight, or hummed a tune in your head, you have brushed against algebra without knowing it. The way a piano is tuned so that you can play in any key and have it sound right rests on dividing the octave into 12 steps that are equally spaced in a particular multiplying sense, each step a fixed ratio above the last, a ratio that is a special root of 2. That tuning, called equal temperament, is a quiet algebraic compromise, worked out over centuries, that lets all the keys live together in harmony. The music you find restful is sitting on a scaffold of carefully chosen numbers. And if you have ever watched anything animated, a film, a cartoon, a moving image of any kind, every smooth motion you saw was algebra deciding the in-between positions, easing a character from one pose to the next along gently curving paths, described by equations, the same curves Descartes first drew, now setting the timing of a falling leaf or a turning head so that it feels natural to your eye. And then there is the newest place algebra lives, the one being spoken of everywhere now, the machines that seem to learn. When a system recognizes a face, or finishes your sentence, or answers a question, underneath its apparent cleverness is an enormous structure of linear algebra, vast grids of numbers, millions upon millions of them, multiplied together in great cascades, exactly the transforming of vectors by matrices that we met a little while ago. And the way such a system is taught is itself a piece of algebra in the oldest spirit of all. It begins knowing nothing, with all its millions of numbers set at random, and it is shown example after example, and each time it is a little wrong, it nudges its numbers to be a little less wrong, searching, slowly, for the values that make its answers fit the world. It is solving for unknowns, millions of unknowns at once, found not by a tidy formula, but by patient correction, step after step, exactly the spirit of the Egyptian scribe 4,000 years ago, guessing the heap, seeing the error, and adjusting toward the truth. The most modern thing in the world is built on the most ancient idea we followed tonight, the unknown, sought by the rules it must obey. So when we said, at the very start, that the device in your hand was solving equations, that was not a poetic flourish. It was the plainest possible truth, and now you can feel how deep it goes. You are surrounded, tonight, by solved and solving equations, in the air carrying sound to your ears, in the sky placing you on the map, in the locks guarding your messages, in the medicine in your blood, in the walls holding up the dark above you, in the music and the moving pictures, and the quietly learning machines. The whole modern world is a single vast act of algebra, the finding of countless unknowns, the balancing of countless equations, going on ceaselessly and silently while you lie here and breathe, and almost none of it would be possible without the long, slow journey we have traced, from the clay tablets, to the house of wisdom, to the curves of Descartes, and the symmetries of two young men who died too soon. There are a few last ideas worth meeting, gently, before we drift toward the open questions, 3 quiet rooms of the subject we have not yet stepped into, each one a natural widening of everything you already hold. The first is small, but it changes the whole feeling of a problem. All night we have spoken of equations, of things being exactly equal, of the 2 pans of the scale resting perfectly level. But the world is not always about exact equality. Often what matters is not that something equals a value, but that it stays below a value, or above one. A bridge must carry at least a certain weight, a budget must stay under a certain limit, a temperature must remain above freezing, a dose must be enough but not too much. For all of these you do not want a single answer, you want a range of acceptable answers, a whole stretch of values that satisfy the condition. And algebra has a tool for exactly this, called the inequality, which is like an equation but with the level scale replaced by a tilted one side allowed to be heavier than the other, or lighter. Instead of the parallel lines of the equal sign, there is a sign that opens toward the larger side, like a mouth that always swallows the bigger quantity. And you solve an inequality much as you solve an equation, by the same patient balancing, doing the same thing to both sides to keep the relationship true, except for one gentle and famous twist. If you multiply or divide both sides by a negative quantity, the tilt of the scale reverses, the greater becomes the lesser, because to negate is to turn the whole number line end for end, and what was larger, once reflected, becomes smaller. It is a small rule, but it carries a quiet truth, that flipping into the negative reverses the order of things, the way a reflection in still water turns the high hills into low valleys hanging beneath the surface. And from inequalities grows something the modern world leans on constantly, the search for the best possible answer within a set of limits. This is called optimization, and it is one of the most practical things algebra has ever given us. Suppose you have many conditions to satisfy at once, many inequalities, a budget you cannot exceed, an amount you must produce, a time you cannot run past, all of them tilting and constraining at the same moment. Together they carve out a region of allowed possibilities, a kind of fenced field of all the choices that break none of the rules. And then, within that fenced field, you go looking for the single best point, the choice that makes some quantity as large as it can be, the most profit, or as small as it can be, the least cost, the least waste, the shortest distance. This search for the best corner of a fenced field of possibilities is solved by algebra, and it runs an astonishing amount of the world you never see. It decides how delivery trucks are routed so that the fewest miles are driven. It decides how factories schedule their work, how airlines assign their crews, how power is shared across a grid, how a diet can be made cheapest while still meeting every need for nourishment. Every time something in the modern world is done in the most efficient way, the leanest, the cheapest, the fastest, there is very often an optimization quietly behind it, an algebra of the most and the least, finding the best point in a fenced field of the possible. It is a gentle thought that so much of the efficiency we move through each day, unnoticed, is the result of algebra patiently seeking the finest choice among the allowed ones. The second room is stranger and more wonderful, and it follows from Descartes more than anyone. Remember his great gift, the naming of a point on a flat sheet by two numbers, how far across and how far up, two numbers for a point on a plane. And if you wanted to name a point not on a flat sheet, but floating somewhere in the room around you, in the full space of the air, you would need three numbers, how far across, how far up, and how far back. Three numbers for a point in space. This matches the world we can see and touch, the world of three dimensions, and it feels like the natural end of the line. But here is the quiet leap that algebra allows, and that the seeing eye cannot follow. Nothing in the mathematics stops at three. If a point in space is named by three numbers, then a list of four numbers names a point in a space of four dimensions, and a list of five names a point in five dimensions, and a list of 100 numbers, or 1,000, names a single point in a space of 100 or 1,000 dimensions, spaces that no one can ever picture, that the human eye and the human imagination simply cannot enter, and yet that algebra moves through as easily and as surely as it moves through the flat sheet of paper. The symbols do not care that you cannot see it. The rules work exactly the same, no matter how many numbers are in the list. You can measure distances in these unseeable spaces, and speak of directions in them, and find the nearness of one point to another, all by pure algebra, all without ever forming a picture, because the algebra was never really about pictures in the first place. The picture was only ever a kindness, a way of helping us along for the first 2 or 3 dimensions. Beyond that, we let go of the picture, and we trust the symbols, and they carry us into spaces of any size at all. This is not a mere curiosity, it is the secret behind a great deal of what the learning machines of today actually do. When a modern system handles language or images or your tastes and preferences, it does so by turning each thing into a long list of numbers, a point in a space of hundreds or thousands of dimensions, where the position somehow captures the meaning. Words with similar meanings end up as points near one another in this vast, unseeable space. Songs you might love sit close to the songs you already love. Faces that resemble each other land in the same region, and the machine reasons about all of it using exactly the algebra of distance and direction that Descartes began with 2 little numbers on a sheet of paper, now stretched out into 1,000 dimensions. The whole inner life of these systems takes place in spaces no one can ever look at, navigated entirely by the algebra of lists of numbers. So that simple act, naming a point by how far across and how far up, turned out to be a door. And behind the door were infinitely many rooms, each with one more dimension than the last, stretching away further than sight or imagination can go. And algebra walks among them all without ever needing to see. And the third room is really a doorway, a place where this whole subject opens out into the one that comes after it, so that you can feel where the road leads if you keep walking. Everything we have done tonight, in a sense, has been about the still and the fixed, the unknown that has one settled value, the balance that holds, the curve that sits drawn upon its plane. Even the functions, the machines of dependence, we have mostly looked at as finished shapes. But the world is not still. The world moves, and flows and changes from one instant to the next. The car speeds up and slows. The temperature rises and falls. The population grows. The wave climbs and breaks. And to capture change itself, the very motion of things, algebra had to grow one more time into a new subject, built directly on top of everything we have spoken of, a subject called calculus. I will not lead you into it tonight, because it is its own long country, deserving of its own quiet night. But I want you to feel the doorway, to know it is there. Calculus is what you get when you ask algebra, not what a quantity is, but how fast it is changing, at a single frozen instant, and when you ask how countless tiny changes, added up, accumulate into a great whole. It is the mathematics of the steepness of a curve at one exact point, and of the area beneath a curve gathered from infinitely many slivers, the very kind of endless gathering we touched when the halving steps added up to one. It was brought into the world in the same era as Descartes' later years, by Newton and by Leibniz, working separately, and it could not have existed without the algebra and the coordinates and the functions that we have walked through tonight as its foundation. So if this road we have traveled feels by now like a complete and finished thing, know that it is also a beginning. Just past the edge of tonight lies the algebra of change, of motion, of the living, flowing world, waiting on the far side of the doorway, for some other night when you are more awake. For now, it is enough to know the doorway is there, glowing softly at the end of the long hall we have walked, and that you may pass through it whenever you wish. Now, as the night deepens, let us turn toward the edges of what is known, because even now, even with all of this power and reach, algebra has not run out of mysteries. There are questions at its frontiers that the finest living minds cannot answer, and there is something restful in that, something that lets the mind wander without strain. So let us drift for a while through a few of the beautiful unsolved and strange things, not to trouble you, but to give your thoughts somewhere soft and open to roam as you fall. The first of these is a story that took 350 years to end, and it is one of the most famous in all of mathematics. Long ago, in the 1600s, that French thinker we might not have named yet, Pierre de Fermat, a man who did mathematics for pleasure in his spare hours and rarely bothered to publish, was reading an old copy of the very Arithmetica, written by Diophantus, the same Diophantus from Alexandria we met early tonight. In the margin of his book, beside a problem about whole numbers, Fermat scribbled a note. He claimed that a certain kind of equation, a simple-looking one about whole numbers raised to powers, had no solutions in whole numbers at all once the power went above 2. And then he wrote the most tantalizing sentence in the history of the subject. He wrote that he had found a truly wonderful proof of this, but that the margin was too small to contain it. And then he died, and no proof was ever found among his papers. For 3.5 centuries, the greatest mathematicians on earth tried to prove what Fermat had so casually claimed in the margin. They tried, and the problem defeated every one of them, becoming the most famous unsolved problem in mathematics, a kind of beautiful taunt left behind by a man long dead. It was finally proven true at last, in the 1990s, by an English mathematician named Andrew Wiles, who worked on it in secret for 7 years, alone in an attic study, drawing on vast machinery of modern algebra that Fermat could never have imagined. The proof runs to over 100 pages of the most advanced mathematics. So almost certainly, Fermat did not really have the simple proof he claimed. He was probably mistaken, or fooling himself, in that margin so long ago. But his idle note set in motion 3.5 centuries of effort that built whole new branches of algebra along the way. Sometimes a question is a gift, precisely because it is so hard. because of all the things people must invent in the long struggle to answer it. Near to this lies a question even stranger and more humbling, about the limits of algebra itself. We have spent tonight celebrating the finding of unknowns, the solving of equations. But there is a particular kind of equation, named after Diophantus once again, the kind that asks only for whole number answers, no fractions allowed, only clean whole numbers. And a great mathematician named David Hilbert, at the dawn of the 20th century, posed a sweeping challenge. He asked whether there could be a single universal method, a step-by-step procedure of the kind al-khwarizmi first dreamed of, an algorithm that could take any such whole number equation at all and decide, with certainty, whether it had any whole number solutions. A master key for an entire universe of problems. For 70 years people searched for this master key, and then in the 1970s it was proven, through the work of several mathematicians, that no such key can ever exist. There is no universal method. The realm of whole number equations is so wild, so endlessly varied, that no single procedure can ever tame all of it at once. Some questions in that realm can be answered, but there is no recipe that answers them all, and there never can be. It is a strange and quiet kind of awe, to learn that algebra contains regions that algorithm can never fully conquer, that the unknown, in some of its deepest forms, keeps a permanent privacy, forever beyond any single method to reveal. There is a related mystery at the very heart of computing, perhaps the greatest unsolved question in the whole field, and it touches everyone tonight whether they know it or not. It concerns the gap between finding an answer and merely checking one. There are many problems where, if someone hands you a solution, you can check that it is correct very quickly and easily, but where finding that solution in the first place seems to require a search so vast it could take longer than the age of the universe. The scrambling of your messages relies on exactly this gap. But here is the thing. No one has ever proven that this gap is real. No one has ever proven that these problems truly are hard to solve, rather than merely hard for us, so far, because we have not yet been clever enough to find a fast method. It remains an open question whether every problem whose answer is easy to check is also, secretly, easy to solve, if only we knew how. Almost everyone believes the gap is real, that some things are genuinely hard to find, even when easy to verify. But belief is not proof, and the question stands open, with a fortune offered to anyone who can settle it either way, and the security of the entire digital world quietly resting on an assumption no one has been able to confirm. And then there are the questions that are not really mathematical at all, but that the long history of algebra keeps pressing upon us. Questions about what mathematics even is. Think back to those imaginary numbers, the ghosts that appeared in the Italian solving of cubics, the square roots of negatives that everyone agreed were absurd and useless. Centuries later, those very same impossible numbers turned out to be the exact and necessary language for describing electricity and light and the deepest behavior of matter at the smallest scales. The strange rules of the quantum world, the actual physical reality underlying everything you can see and touch, cannot be written down properly without those imaginary numbers. So a piece of pure algebra, invented reluctantly, dismissed as a meaningless fiction, was waiting, it seems, for reality to catch up to it, and reality did. This happens again and again in the history of the subject. Abstract structures, dreamed up by mathematicians for their own beauty, with no thought of use, sit quietly for decades or centuries, and then turn out to be precisely the shape that some corner of the physical universe was wearing all along. And this raises a question no one can answer. Is mathematics something we invent? A game of our own making, that just happens to be useful? Or is it something we find, already there, woven into the fabric of reality, waiting to be uncovered the way a continent waits to be reached? When a young man scribbles down a new kind of symmetry the night before he dies, and a century later, that very symmetry is found to govern the particles that make up the stars, it becomes very hard to believe we are only inventing. It begins to feel as though we are remembering something the universe already knew. Let your mind drift back, now, over the long road we have traveled, because there were travelers on it we passed quickly in the dark, and they deserve a quiet word before the night closes in. We followed one path tonight, from Babylon through Baghdad to Italy and France, but algebra grew in more places than that, and in some of them it grew earlier and further than the story usually tells. Far to the east, in ancient China, mathematicians were doing algebra of remarkable sophistication 2,000 years ago, quite independently of the West, written in a great work whose title means The 9 Chapters on the Mathematical Art. It was not the work of one person, but a treasury gathered and refined over generations, and within it lies something extraordinary. The Chinese mathematicians had a method for solving whole systems of equations, many equations in many unknowns at once, and the way they did it would look strangely familiar to anyone who has studied the linear algebra we spoke of earlier. They laid out the numbers of the problem as a grid, using small counting rods placed on a board, arranging them in neat columns, and then they manipulated the columns, subtracting one from another in careful steps, slowly clearing away unknowns until the answer fell out. This is, in all its essentials, the very same method of organized elimination that the West would not write down until Gauss, nearly 2,000 years later. They had the heart of it, on a board of bamboo rods, in the time of the Han Dynasty. And they did one more thing that the West would resist for centuries. They used negative numbers freely and without anxiety. On their counting boards, they used rods of one color for positive quantities and another color for negative ones, red and black, and they combined them as easily as a merchant combines profits and debts. While European mathematicians were still calling negative answers absurd and impossible, the Chinese had been working with them comfortably for over 1,000 years, simply as a matter of which color rod you reached for. It is a quiet lesson in how knowledge is not a single river flowing one way, but many streams, rising in many lands, some of them far ahead of others, all of them feeding, in the end, the same sea. In India, beyond the work of Brahmagupta whom we met earlier, there came another great figure some centuries later, a mathematician named Bhaskara, sometimes called Bhaskara the Second, to tell him apart from an earlier man of the same name. He lived in the 12th century, and he wrote works of both deep mathematics and real charm, including one named lovingly after a young woman, perhaps his daughter, with problems posed in gentle poetic language, asking about bees among lotus flowers and necklaces of pearls. Beneath the poetry was serious algebra. Bhaskara understood the two answers of a quadratic, the positive and the negative twin. He worked fluently with zero and with negatives, and he developed a beautiful cyclic method for solving a certain hard class of whole number equations, a method that would not be matched in Europe for 600 years. He stands as a reminder that the long centuries we sometimes pass over quickly, between the ancient world and the European Renaissance, were not empty at all. They were full of patient brilliance, in India and in the Islamic world and in China, keeping the flame and feeding it, so that when Europe finally took up the torch was already burning bright. There was another quiet revolution too, in the early 1600s, just as the language of symbols was being settled, and it concerned not the solving of equations but the easing of calculation itself. A Scottish landowner, named John Napier, working for 20 years on a problem of pure patience, gave the world a tool called the logarithm. The idea behind it is a piece of deep algebra about powers and exponents, but its effect was wonderfully practical. Napier found a way to turn the hard labor of multiplying two large numbers together into the much easier labor of adding two other numbers, by means of carefully prepared tables. For astronomers and navigators, who had to multiply enormous numbers by hand night after night to track the stars and find their way across oceans, this was an extraordinary relief. It was said that Napier, by halving the labor of calculation, had doubled the lifespan of the astronomer. For nearly 400 years, until the electronic calculator arrived, the logarithm and the sliding rule built upon it were the constant companions of every scientist and engineer, the quiet algebra that lay behind every bridge designed and every voyage charted. and the same deep relationship between adding and multiplying that Napier harness sits, even now, inside the way your devices handle very large and very small numbers, and inside the way we measure the loudness of sound and the strength of an earthquake and the acidity of a liquid. The logarithm is everywhere, a gentle ghost of 17th century arithmetic, still easing calculation in the dark. And there is one more traveler to greet, who comes much later, in the early 20th century, and who more than almost anyone shaped the abstract algebra of structures that we spoke of, the study of groups and rings and fields. Her name was Emmy Noether, a German mathematician of towering ability, who worked in a time and place that made things very hard for a woman who wished to do mathematics. For years she was not allowed a proper paid position and lectured under a male colleague's name, simply because the universities of her day would not formally employ a woman. And yet her ideas were so powerful that the greatest mathematicians of the age fought for her right to teach, and she became the central figure in the development of modern abstract algebra, the person who taught the world to think about these structures in their cleanest and most general form. Much of the way algebra is understood and taught today flows from her vision, but she gave the world something even beyond that, a single result so deep that it changed physics forever. She proved that there is an exact and unbreakable link between symmetry and the great conservation laws of nature, the laws that say certain quantities, like energy, can never be created or destroyed, but only moved about. She showed that every continuous symmetry in the laws of physics gives rise to a quantity that is conserved, and every conserved quantity comes from a symmetry. The reason energy is conserved, she revealed, is that the laws of physics are the same today as they were yesterday, and will be tomorrow, a symmetry in time. The reason the momentum of things is conserved is that the laws are the same here as they are over there, a symmetry in space. The deepest bookkeeping of the universe, the things it never lets change, turn out to be the shadows of its symmetries. And symmetry, as we saw in the work of those two young men who died so early, is exactly what the abstract algebra of groups was built to describe. So the thread we followed from the symmetries of a simple square reaches all the way to the laws that govern the stars, tied together by the work of a woman who was barely allowed to hold a job. Algebra, the art of the unknown, had become the language in which the universe keeps its deepest promises. When she was forced to flee her homeland, as the darkness of the 1930s closed over Germany, Emmy Noether crossed the ocean and continued her work, and continued to gather students around her, generous and warm to the last, until her sudden death only a couple of years later. The man who had reshaped our picture of space and time, Albert Einstein, wrote of her afterward as the most important creative mathematical genius produced since the higher education of women began. Hold her in your mind for a moment, lecturing under another's name, building the cleanest structures of modern algebra, revealing why the universe conserves what it conserves. She is among the last great travelers on the road we have walked tonight, and one of the brightest. So that road, when you stand back and look along its whole length, runs across 4,000 years and the entire width of the world. It begins with scribes pressing reeds into clay by the rivers of Iraq, and with the heaps and false guesses of Egypt. It passes through the counting rods of Han China, already doing in red and black what Europe would take 2,000 years to dare. It moves through the zero and the bold negatives of India, through the careful systems of Brahmagupta and the poetry of Bhaskara. It gathers itself in the house of wisdom in Baghdad, where al-khwarizmi gives the subject its name and its first true method, restoration and balancing. It travels with the merchant Fibonacci across the sea into Europe, bringing the very digits we still write. It bursts into drama in Renaissance Italy, with the secret of the cubic and the feud it caused, and the first glimpse of the impossible imaginary numbers. It is given a clean written language by Ricordi and Viette and Descartes, who also weds it to geometry and lets us see equations as shapes. It is eased by Napier's logarithms, lifted into the study of pure structure by the 19th century, and brought to its sharpest questions by Abel and Galois, who show us, at the cost of their young lives, where the limits of solving lie. And it flowers in the modern age through Noether and those who followed, becoming the language of symmetry, the language of the deepest laws of nature, and the silent engine of every machine around you. One single idea, the hidden number found by the rules it obeys, grown across millennia into the very grammar of the universe. That is the road, and you have walked all of it tonight. And here is something gentle to rest your mind on as you look back along that road, a hidden pattern that ties the whole journey together, a pattern not in the people, but in the numbers themselves, because the numbers grew along this road. They were not always as many as they are now. The very idea of what counts as a number kept being forced to grow larger, again and again, and each time it grew for the same reason. It grew because someone wrote down an equation that had no answer and refused to accept that there was none. Let me show you this slowly, because it is one of the most quietly beautiful things in all of mathematics, and it gathers up almost everything we have touched tonight into a single rising shape. In the very beginning, there were only the counting numbers, 1, 2, 3, and onward, the numbers you use to count sheep, or stars, or days. They are the oldest numbers, older than writing, older than history. For a long time, they were all the numbers there were, and for simple counting, they are enough. But then someone asked a question that broke them. Someone wrote down, in effect, a little equation. What number, added to 5, gives 3? Among the counting numbers, there is no answer. You cannot count your way from 5 up to 3, because 3 is smaller. The question seems absurd, a dead end. And for a long time, people treated it as exactly that, an impossible problem, to be thrown away. But the question would not go away, because the world kept asking it, in the form of debts, of temperatures below the freezing point, of distances in opposite directions. And so, slowly, painfully, with all the resistance we have traced through the Greeks and the centuries of European doubt, the answer was allowed into existence. The answer is a negative number, and to make room for it, the family of numbers had to grow. The counting numbers and their negative reflections and the zero between them together formed a larger family, the whole numbers stretching out in both directions from 0 into the positive and the negative alike. The number line grew a second half, reaching out behind 0 into territory the ancient world had called impossible. And it grew because an equation demanded an answer, and people finally chose to listen. But the new family, large as it was, could still be broken by a single question. What number, multiplied by 2, gives 1? Among all the whole numbers, positive and negative, there is none. You cannot reach exactly 1 by doubling any whole number. The question points into a gap, a space between the whole numbers where no whole number lives. And again, the world kept asking it, every time something had to be shared, a single loaf among 3 people, a single field among 4 heirs. So again the family of numbers grew, to admit the fractions, the ratios of one whole number to another, filling in the spaces between the whole numbers with an endless fine dust of new values. Between any 2 whole numbers there now lived infinitely many fractions, packed in tightly, so that the number line, once a row of separate stepping stones, became almost a smooth and continuous thread. These ratio numbers, the rationals, seemed at last to be everything. They were so dense, so finely packed, that the ancient Greeks who loved them believed, deeply and almost religiously, that these ratios were the very fabric of the world, that everything in the universe could be captured by the ratio of one whole number to another. They built a whole philosophy on it, and then came the question that shattered that faith, and it is one of the most dramatic moments in the history of thought. The Greeks, following the school of Pythagoras, knew a simple fact about a square. If a square has sides of length 1, then the diagonal across it, corner to corner, has a definite length, a real and drawable length you can measure with a ruler. And they asked the natural question, what is that length? They expected, as they expected of everything, that it would be a ratio, some fraction of whole numbers, but it is not. The length of that diagonal, the square root of 2, the number which multiplied by itself gives exactly 2, cannot be written as any ratio of whole numbers at all. It is not a fraction, and it never will be, no matter how large the numbers you try. There is a proof of this, clean and final, that the Greeks themselves found, and it must have struck them like cold water. A perfectly ordinary length, the diagonal of the simplest possible square, sitting right there to be measured, was not a ratio. It fell into a gap that they had believed contained nothing, a gap between the fractions, hidden in the fine dust of the number line. There is an old and probably half-legendary story that the man who first revealed this terrible secret, a follower named Hippasus, was drowned at sea for it, punished by his fellow believers for unveiling something that broke their entire picture of the world. Whether the story is true or not, it carries the weight of how shocking the truth was. The ratios were not everything. There were numbers in between them, numbers that no fraction could ever name, and to hold the diagonal of a square, the family of numbers had to grow yet again, to include these strange, unnameable values, the irrational numbers, the ones that go on forever, after the decimal point, without ever falling into a repeating pattern. With them added in, every last gap on the number line was finally filled, and the line became truly smooth and unbroken, a perfect, continuous thread from the depths of the negative to the heights of the positive. This complete, gap-free collection is what we call the real numbers, and for most purposes, it feels like the end of the story. It feels like all the numbers there could ever be, but you already know, from earlier tonight, that it is not the end, because there is one more question, the deepest of all, that even the smooth and complete real numbers cannot answer. What number, multiplied by itself, gives -1? We met this ghost in Renaissance Italy. Among all the real numbers, every single one, when multiplied by itself, gives a positive result, or 0, never a negative. So this question, like all the others before it, points into emptiness, into a place where the current numbers say there is nothing. And just as before, mathematics eventually chose not to accept the emptiness, but to grow into it. It declared that there shall be a number whose square is -1, the imaginary unit, and it built, on top of that single bold declaration, a whole new and larger family, the complex numbers, where every number has two parts, an ordinary real part and one of these new imaginary parts, woven together. And here, at last, something final and beautiful happens, the thing that the fundamental theorem of algebra promised us earlier. Once you have grown the numbers all the way out to the complex numbers, the growing stops, because in this final, largest family, every polynomial equation, every single one, of every degree, has all of its solutions waiting inside. There are no more broken questions. There is no equation you can write, using these numbers, whose answer falls outside of them. The family is complete. The long expansion that began when someone first asked what number added to 5 gives 3. The expansion that was forced outward step after step across thousands of years comes at last to rest. The numbers have grown exactly large enough to answer every question that algebra can ask of them, and not one bit larger than they need to be. So that is the hidden shape beneath the whole journey, the secret pattern in the numbers themselves. 5 times the family of numbers grew, and every single time, it grew because an unknown demanded to exist. The counting numbers, broken by subtraction, grew the negatives. Broken by division, they grew the fractions. Broken by the diagonal of a square, they grew the irrationals and became the smooth real line. Broken by the square root of a negative, they grew the imaginary and became complete. Each new kind of number was not a free invention, not a thing dreamed up for amusement. Each one was an answer that the world insisted must exist, pulled into being by an equation that refused to have no solution. The unknown did not just sit and wait to be found. The unknown reshaped the very idea of number, 5 times over, each time forcing the universe of mathematics to grow larger and more generous, until it was wide enough to hold every answer. That is what algebra truly did, across all those centuries. It did not only find hidden numbers, it expanded what a number could be. By now you may have drifted in and out a few times. That's exactly right. There's nothing to catch up on. Everything has been settling quietly whether you were following closely or not. So let everything we have walked through tonight settle now into one single picture, the way a stirred pool grows still and becomes a clear mirror. If you were to hold all of tonight in one image, it would be this: a balance. A simple set of scales hanging level in the dark, with something known resting in one pan and something unknown resting in the other, the two held in perfect equality across the quiet pivot between them. That is what algebra is, at its very root, underneath every formula and every curve and every grand abstraction. It is the art of the balance between the known and the unknown. It is the willingness to place a thing you do not yet understand onto the scales opposite the things you do understand, and to trust that the balance between them will lead you, step by patient step, to the unknown's true name. Everything else tonight was only this one idea, growing. Watch how it grows, all at once, in this final still image. It begins with a single act of courage, the act of giving a name to something you do not know, a letter, standing in the dark for a number not yet found. This is the seed of everything, the variable, and it is a stranger act than it first appears, because to reason about a thing before you know what it is requires a kind of faith, a faith that the unknown is nonetheless lawful, that it obeys rules even while it hides. From that single seed you build a phrase, an expression, a little construction of the unknown woven together with the known by adding and multiplying. And then you make a claim about that phrase. You set it equal to something, and the claim becomes an equation, a sentence, a balance asserted across the pivot of that equals sign which Robert Ricord drew as two lines that can never disagree. And the moment the balance is asserted, the whole machine comes alive. Because now there is exactly one thing to do, the thing al-Khwarizmi named 1200 years ago in Baghdad: restore and balance. Do the same to both sides, always the same, never breaking the level of the scales, peeling away the known weights one by one until the unknown stands alone in its pan and reveals, in the opposite pan, precisely what it was all along. That is the beating center. Everything that came after is this same heartbeat, made larger, because then the unknown learns to multiply by itself, and the balance becomes the quadratic, with its twin answers born from the folding of the square, solved by the literal carpentry of completing the square, the moving of tiles until the shape is whole, the same carpentry done in the sand of Baghdad, and remembered now as a formula, so that no one need cut the tiles again. And then the unknown is set free entirely, allowed to roam through all its values, and as it roams its answers trace a shape upon the plane that Descartes laid down, and suddenly the balance is not a single point but a whole curve, a line, a sweeping parabola, a living picture in which algebra and geometry are revealed to have been one thing wearing two faces all along. The equation becomes a shape. The shape becomes an equation. And once you can see the unknown's behavior drawn out before you, you can ask where it climbs and where it falls and where it rests, and from those questions grows the function, the faithful machine of dependence, the basic word in which every science describes how one thing follows from another, how distance follows from time, how the world unfolds from its causes. And still it grows, two unknowns at once, tangled together, pinned down where their curves cross, and that crossing is how your phone finds you beneath the satellites tonight. Many unknowns at once, gathered into grids of numbers that stop being tables and become transformations, machines that turn and stretch all of space together. And that is the algebra that draws every moving image and ranks the whole web, and squeezes a song small enough to send. And then the greatest leap of all, the moment algebra lifts its eyes from numbers entirely and begins to study the rules of combination themselves, the structures, the groups, the symmetries, asking not what number solves this, but what is the deep shape of the solving, and finding that this shape, this symmetry, is the very thing that decides which equations can be solved at all, and is also, by Emmy Noether's hand, the very thing that decides what the universe is forbidden ever to change. The art of the balance between the known and the unknown had become the language of symmetry, and the language of symmetry turned out to be the language in which the laws of nature are written, from a name given to a hidden number all the way to the conservation of energy itself, in one unbroken line. And beneath all of that growing, as you saw just now, the numbers themselves were growing too, forced outward step by unknowns that demanded to exist, from the counting numbers to the negatives to the fractions to the irrational diagonal of a square to the imaginary root of a negative. Each new kind of number pulled into being by an equation that refused to have no answer, until the family of numbers was finally wide enough to hold every solution algebra could ever ask for. So the unknown did two things at once across all those centuries. It taught us to find what is hidden, and in the very same motion, it stretched the boundaries of what could exist, what could count as a number, what could count as a quantity, what could count as real. The diagonal of a square was always there to be measured, but it took an equation to admit that the number naming it was real. The behavior of electricity and light was always there, but it took those impossible imaginary numbers, born in a Renaissance feud, to give it a voice. Again and again, algebra reached past the edge of the accepted world and found that the world was larger than people had dared to believe, and that the strange new numbers it was forced to invent were not fictions at all, but were waiting, all along, for reality to be seen clearly enough to need them. This is the thing to hold, then, as the night grows deep. Algebra is not the rows of symbols that may have troubled you once in a bright and hurried classroom. Those symbols were only the handwriting. The thing itself is far older and far gentler than that. It is the simple, profound human decision to reason about what we do not yet know, by trusting that the unknown obeys laws, and by balancing it patiently against the known until it yields. It is 4,000 years of people, in clay and on papyrus, in Baghdad and Bologna, and on the counting boards of China, choosing not to be stopped by a question that seemed to have no answer, choosing instead to grow the world until the answer had a place to live. It is, in the end, a quiet form of hope, made rigorous, the hope that the hidden can be found, the hope that what balances can be solved, the hope that even the things we cannot yet name are lawful and patient and waiting, on the other side of the scales, to be brought gently into the light. And the most restful part of the whole picture is this: you do not have to do any of it tonight. Every one of those balances, in your phone, in the sky, in the walls, in your own quiet body, is already solved, or solving itself without you. The vast machine of found unknowns is humming along in the dark all around you, asking for nothing, holding everything in its proper place. You spent your whole life inside it without needing to see it, and now you have seen a little of it, and you can let it go again, and it will keep working all the same. The balance does not need you to watch it to stay level. It simply stays level, through the night, on its own. So let your attention come back, softly, from the wide sweep of all that history, back to the small and quiet place where you actually are, back to this room, back to the weight of your own body against the bed, back to the device, somewhere near you, that has been speaking all this while. Remember what we said about it at the very beginning, when the night was younger and you were more awake. We said it was solving equations to bring you this voice. Thousands of them, every second, filling in the unknown spaces between the numbers it had stored, working out the values it could not see directly, so that a smooth and human sound could reach your ears in the dark. It has been doing that, without pause, through every word of tonight, through the clay tablets and the house of wisdom, through the Italian feud and the curves of Descartes, through the two young men and the growing of the numbers. It was there in your hand the whole time, quietly finding unknowns, so that the story of finding unknowns could be told to you. There is a gentle circle in that, the thing describing itself, the balance solving for the words that explain the balance. You do not need to do anything with the thought. Just let it rest there, turning slowly, like something warm. And it is not only the device. Feel, if you can, without effort, how much else is being quietly solved around you right now. The air in the room has been settling toward a single even temperature all night, every part of it balancing against every other. an equation of heat working itself out so slowly and so surely that you never felt it happen. The walls above you are holding their load in perfect silent balance, every force answered by another force, the whole structure resting in a solution that some engineer found years ago and that has held true every night since, including this one. Far above the roof, the satellites are still circling, still calling out their patient signals into the dark, ready to place anyone who asks at the single crossing point of their invisible spheres, though you are not asking, because you are not going anywhere tonight. You are exactly where you mean to be. And inside you, in the warm dark of your own body, the same lawfulness is at work, the chemistry settling toward its balances, the rhythms finding their steady values, everything tending, as you lie still, toward rest. There is something steadying in knowing that all of this holds without your attention. The balances do not require you to be awake. The unknowns go on being found whether you follow them or not. The whole vast machinery of solved equations that cradles you tonight asks nothing of you at all. No effort, no watching, no understanding. It held you last night while you slept and understood none of it, and it will hold you tonight just the same, now that you have glimpsed a little of how it works. Understanding it changes nothing about how safely it carries you. It was always carrying you. Tonight you simply got to see, for a little while, some of the quiet machinery underneath the floor of the ordinary world. And now you can let the floor close over again, and trust it, and sink. Think, if any thought is still moving in you at all, of that first idea, the oldest one, the one the scribes had 4,000 years ago by the slow rivers. The idea of a thing you do not know, that you are nonetheless willing to reason about, trusting that it obeys quiet laws, even while it hides. There is something in that idea that reaches beyond mathematics entirely, something almost like a way of meeting the whole of life. So much of what lies ahead of any of us is unknown, unnamed, not yet found. And the oldest lesson of algebra, underneath all the symbols, is simply that the unknown is not the same as the unknowable, that what hides can often be found, patiently, by holding it against what we do know, and keeping the balance, and not being frightened off by a question that seems at first to have no answer. The people in this story were not stopped by the impossible. They grew the world until the impossible had a place to stand. You can let that settle into you, gently, as more than mathematics, a quiet trust that the hidden things are lawful, and patient, and findable, in their own time. But you do not need to hold even that. You do not need to hold anything now. The night has grown deep, and there is nothing left to follow, and nothing left to understand, and nothing at all that you must do. Every idea from tonight will still be here in the morning if you want it, settled quietly into you whether you were listening closely or drifting far away. Nothing is lost by sleeping. That was the whole point, from the very first words. The ideas keep, the balance holds, the night does the rest. So let the last of your attention loosen now, like a hand slowly opening. Let the scribes set down their reeds. Let the scholars close their books in the house of wisdom, and let the lamps there go dark. Let the curves on Descartes' plane fade softly back into the white of the page. Let the two young men rest, their work safe now, carried on by others, nothing more for them to prove. Let the numbers stop their growing, and simply be, complete, exactly wide enough, needing nothing more. Let all of it grow quiet and small and far away, like a town seen from a great height at night, all its little lights going out one by one. The unknown is found, the balance is level, the long road is walked, all 4,000 years of it, and you walked it, and now you can lay it down. There is nothing more to solve tonight. Everything that needed balancing has come to rest, including you. Let your breath go slow. Let the room go soft and dim. Let the quiet machinery hum on without you, finding its endless unknowns in the dark, while you, the one thing it was all quietly holding, finally let go, and drift, and sleep.